Hello. Okay, we're back. So the stream is back. I'm also back. Welcome back to the live stream, everyone. I'm Lily. I'm your host for this 19th hour of our 100-hour live stream to save America's forecasts. I'm a PhD student studying atmospheric and climate science, and uh, to get started, so as we're waiting for more people to trickle in, one thing I really want to know is what's your favorite science fact that you've learned in the last 19 hours? Like, people have been super excited about all the talks. I want to know what's your favorite new weather and climate fun fact. Okay, and also going to go through my little spiel, which is that before we move on to our next speaker, I want to start off with a quick reminder of why we're doing this live stream. Why is that? To save America's forecasts. And what that means is like we really believe that all Americans deserve good weather and climate forecasts. And in fact, US scientists have been at the forefront of weather and climate predictions for a really long time now. We developed the first computerized weather forecast. We ran the first computer models, like modeling climate impacts of CO2 pollution. And we have this like amazing unparalleled network of observations that's made possible by all these decades of federal investment. So that is to say, it's all thanks to you, the American public. And with US federal funding for science being so essential, we want to highlight the fact that there are these ongoing funding cuts that are affecting all areas of weather and climate science. Earlier yesterday, we heard from some former NOAA employees who were terminated from their jobs, like talking about how much they love being able to serve all Americans and like provide these really crucial forecasts and warnings. So we're hosting this 100-hour streamathon to spread the word that weather and climate science saves lives. And if you'd like to help us save our forecasts, please share our live stream and everything you're learning with not only like your social media circles, but also like your friends and family and your representatives. And if you don't know how to contact your representatives, we've made it very easy for you. You can go to wclivestream.com/act and you can put in your zip code. It'll give you a script about our issue and like the numbers of all your representatives. Just reading your fun facts now. So for anyone who's just tuning in, I want to hear your favorite science fun fact that you've learned from our live stream. Uh, Something about heavy metal exposure and antibiotic resistance. Very cool. Wind direction is different between hurricanes and cyclones. Great. So yeah, keep those coming, guys. And I'm now going to introduce our next speaker, Dr. Stacy Porter, who's an assistant professor at Wittenberg University. And also a brief reminder that all our speakers today for the rest of the 100-hour live stream are appearing in their personal capacities and expressing their own views, which may not be that of other participants or like representing their official positions. Okay, take it away, Stacy.
Thank you so much, Lily, and thank you to all the organizers for putting this together. I wanted to talk just a little bit today about some of the work that I get to do in my small Midwestern city of Springfield, Ohio, which is now a little bit more famous than it used to be. But to give you a little background on me, I was born and raised in East Tennessee, and I grew up loving the weather. I had my own little weather diary. I was also pretty terrified of storms and tornadoes, but I knew I wanted to, dedicate my life to understanding weather. And so I went to the University of North Carolina in Asheville for my bachelor's and really got involved with climatology and studying climate change as well. And so I went to the University of Alaska in Fairbanks for my master's to study how cruise ship emissions are affecting the landscapes and air quality in the Gulf of Alaska. And then I really fell in love with the Arctic. And so I moved to, ironically, to study the Arctic, moved to Ohio to do my PhD research in ice cores and ice core paleoclimatology. And I did a postdoc there at Ohio State as well. And now I'm primarily in a teaching position at an undergraduate institution. So even though I don't rely as heavily on federal funds these days, I wouldn't be here if I didn't have that federal funding through graduate school. And I'm going to show, a project today that I've been working on with students. And even though it's not directly funded by federal research, we rely on these observations from federally funded programs. And we had aspirations of building this out and hopefully getting funding to scale up some of this work as well. So to jump in, one thing we were interested in is looking at the urban heat island in our small Midwestern city of Springfield, Ohio. And so when we talk about an urban heat island, I've got a schematic up here that just shows you different landscapes and how temperature varies across those landscapes. It's a little bit abstract here, but you can see we've got this sort of heat dome over the city area. And that's due to several different things. It's dark roads and parking lots in our cities absorbing more sunlight. It's dark rooftops of these buildings. The buildings themselves, the materials can retain heat. That's cement and asphalt. We have fewer trees, fewer vegetation in our city centers. And we have excess heat from factories and cars. Think about how hot your car gets after you've driven a little bit. And think of all those cars in a city center. And then we also have these impervious surfaces, so surfaces that don't absorb water, right? So think of cement versus soil, right? Soil will retain some of that moisture, and we need that moisture to help keep us cool, just like we sweat to stay cooler. Our landscapes need to do that as well, but asphalt can't sweat. So we see our cities a little bit warmer than those areas around them. And this is an image of Washington, D.C. You can see the satellite image here and then compare it to the temperatures that we see. And you can see a connection there between where we have sort of the heart of the city and where those warmer temperatures, those reds and yellows are, compared to where you see more vegetation, where you see water bodies. It tends to be much cooler in those outlying areas. So why we care about the urban heat island, it can cause illnesses. There's lots of heat-related issues, whether it's heat stroke or exhaustion, or even exacerbating cardiovascular issues. We even see sometimes increased aggression. Heat can affect the serotonin levels in our brains and cause higher crime rates sometimes. We also see increased energy use. So the more the temperatures go up, the more we run our air conditioners to keep it cooler, and that can strain the electrical grid. And we also see impaired air quality. So poor air quality because of some of that heat, the formation of smog or ozone can occur. Because we're also using more energy running our air conditioners, we also see more pollutants like greenhouse gases as well. And then, of course, if we see impaired air quality, it goes back to more illnesses as well. So all of these are sort of interrelated. So I wanted to kind of get my students aware of this issue. And so I would have them go outside onto our campus and look at the temperatures of different surfaces. And so this is just an example here where you see a photograph of our part of our Frisbee golf course and an infrared image, so measuring the heat that we can't really see. And you can again see where we've got some of that bare earth. It's much warmer compared to where we have, trees, where we've got shading, much cooler there. So we're starting to conceptually see why our cities might be a bit warmer. So we wanted to look at Springfield a little bit more broadly. So these are some pictures of our city center, and you don't see a lot of vegetation. It is pretty dense, even though it is a small city. So to explore that, we're using, again, federally funded satellite data. So This is showing not necessarily a satellite image, but showing you the land cover of Springfield here. So where you see all that red, that's what we call built environment, or essentially those buildings and roads and things like that. And then we've got the temperature over here as well. So you can see again that connection between where you have that built environment and where you have warmer temperatures. And the reason this isn't centered right on Springfield is because Wittenberg owns a little bioreserve just south of the city that we call Seabees Place. And it's going to be small to see on the screen there, but it's just at the very bottom of those images. And so if we draw sort of a transect, if we imagine ourselves walking from that little bioreserve called Seabees Place into the heart of Springfield and measure the temperature all along the way, we get to see these variations based on that landscape. And so this is a graph showing those temperatures for 3 different years. And we can see roughly that the city is sometimes 18 degrees warmer than the outlying areas. That's a pretty substantial urban heat island. So we wanted to think about that even further, right? We wanted to see, how does that 18-degree difference impact other aspects of our weather and climate? And so one thing we wanted to look at was precipitation, right? We know warm air rises, right? It's less dense. So if we've got this hot pocket of a city and we've got warm air rising from it, how does that influence, let's say, weather systems as they move through? If we've got a storm coming through, does that elevation, that warm upflow, give a little boost to some of that precipitation? And this is something that's been studied in big cities like Shanghai and Paris and Atlanta, but we've never really looked at it on a smaller scale for a small city. So we wanted to see if, okay, let's look at sort of the windward side of the city compared to the downwind side. And our winds are typically from the west. So we wanted to see, well, do we get a boost on the eastern side of the city? So to look at this, my student and I, Deza, we put rain gauges all around Springfield and even some of those really rural areas to see if we could try to capture some of this. And this was the summer of 2023 that we did this. And I'll admit we put a lot of rain gauges on public land, and a lot of our equipment was stolen. We lost a lot of good rain gauges that summer. But we tried to progress nevertheless, and we used some radar data to help us with some of this interpretation as well. So looking at the radar reflectivity, we were sort of looking at that eastern side to see if we saw more precipitation there. And we didn't really see a connection going from west to east, but we did see one going from south to north. So that's something we really wanted to study a little bit further. And there's multiple reasons for why that might be. I won't get into it in this talk, but we have some running theories as to why that might be. So if we're thinking about, our city being 18 degrees warmer than these outlying areas and all of the impacts that could possibly have even on our precipitation, we want to think about solutions to some of this urban heat. And there's lots of solutions going around, whether it's painting pavement white to make it more reflective and keep it cooler, doing the same thing for roofs, painting those white to make them cooler. We've also seen green roofs coming about, so where you actually have vegetation on top of the building. And then just more green space in general. And so that's sort of the low-hanging fruit for our community. We tend to see lots of people love trees, and so there's a calling out, there's a wanting for more green space in our city. So we thought, well, let's see if we can look for places where we can implement maybe more green space to cool down our city a little bit. So one of the things we have to acknowledge in Springfield is that it was a heavily redlined city, meaning there were racist housing policies that were put in place 100 years ago where banks would not invest in certain neighborhoods simply because there were people of color. And so when we look at these historically redlined communities within our city, we tend to see these areas being lower income, having much less green space, and because of that tend to be much warmer, and as I'll show in a minute, have poorer air quality as well. So this is something I walk through with some of my students as well, to kind of get them familiar with the area that they're in. And, I teach environmental science, so we want to think about our environment as a whole and take that sort of holistic approach. So I've been thankful to work with a nonprofit in Springfield called the Conscious Connect, and it was formed by two Wittenberg graduates. So very, very proud of them. But what they wanted to do is really look to sort of revitalize the south side of Springfield, where we saw some of these heavily redlined communities. And they focus, on many different aspects of life, literacy being a big one for them. But one thing they were also really interested in is the lack of green space on the south side. And so they wanted to explore, some of these inequities in tree cover, in that green space, in access to parks and investment in parks in the south side compared to some of the northern suburbs. And so that's how we sort of got talking about, what are some of these injustices going around in Springfield. So with them, we put together a small proposal to get some of these low cost air quality monitors. They're called Purple Airs, and they're pretty popular these days. And so we've got about 12 of these different monitors that we wanted to place around Springfield. And so to make sure that, because they're relatively low cost, we wanted to make sure that the quality actually was good. So we calibrated them with data from the Environmental Protection Agency's PM 2.5 monitor. That's kind of the gold standard instrument. So we placed all of our sensors on top of a fire station that housed this EPA federally funded monitor. And so then we could see, okay, can we calibrate ours to make sure that it's recording the same thing that this gold standard instrument is? So after doing that, we wanted to place our instruments all around Springfield as best we could. And we wanted to answer a few different questions. How does air quality differ within that opportunity zone, kind of the south side of Springfield, compared to the north side? And then also, how might weather conditions introduce disparities, right? Does it matter what direction the wind is coming from? Does it matter how much precipitation we're getting? How does that change some of the air quality there? So this is where I get my students really heavily involved. And essentially, I've got two classes that focus on this. I've got a first-year seminar, so students who have just arrived on campus, to really give them a sense of community and do this kind of place-based, project-based experiential learning. So they're going out and they're collecting data related to air quality, and they're looking at that history of redlining, and they're seeing some of these injustices in their city, and we're thinking about solutions as well. So it's giving them a little bit of agency. And then I've also got my meteorology class going out and thinking about what are the different weather components and how do those different variables affect some of the air quality that we're seeing. So like I mentioned, wind direction or precipitation, how does that influence the air quality that we see? And so this time we made sure to get volunteers to house some of our equipment, because I didn't want anything to get stolen. So we put a lot of our stuff on private land. We had volunteers who hosted some of those instruments, thankfully, and nothing was stolen this time around. So here's some of the results. This is showing 6 different monitors that we put up around Springfield. And this is also with tree canopy. So that green shading you see is the tree canopy. And so kind of going down the line, we've got those 6. Most of them had relatively good air quality. So that's below about 9 micrometers per meter cubed of that particulate matter. But we had a couple on the south side of Springfield in those redlined communities that had moderate air quality. So a little bit less in quality there. And then we also measured temperature while we were at it. So again, we can start to see those influences of that urban heat island as well, especially when we look at those low temperatures. So sharing results, that's a big thing for our field. We want to make sure we're not just staying in these silos and we're actually getting this information out to the community. So one thing that we did is we put together a little brochure that we could hand out at different outreach events to show some of the results that we gathered from these studies that we did. So whether it was talking about air quality or the heat island, a colleague of mine was looking at soil lead levels and that tree canopy disparity as well. So just kind of put this together. We also had a little QR code for to hopefully gather more volunteers. And this is something we wanted to scale up as well. We were thinking of, if we could get federal funds for this project, could we compensate some of our volunteers to get a little bit more buy-in, to get, a little bit more instrumentation and really get better coverage around the city. So that was something we were really exploring there. And then just to kind of conclude here, but I did want to talk about this thing we did just a few weeks ago. We got together at the local public library and the students got to put posters together and present their results to the community. And that was something they were really, really excited to do. So this is the room we rented at our Clark County Public Library. And you can see members of the community coming out and wanting to know, how does air quality differ in my area? Is it something I need to be concerned about? So, we got to kind of go through all of this and show, yes, we've got an urban heat island in Springfield. We tend to see precipitation being a little bit stronger downwind of the city, although in this case, it's kind of from that south to north. We also see air quality is worse in some of those historically redlined communities. But the thing, that is also really important here is that we were engaging students. So, we were hoping to do some kind of STEM education research with students going forward and seeing how their experience in fieldwork and data collection and analysis grows, whether they're building sort of stronger community ties because they're focusing on this community, they're building agency, they're thinking about these solutions, and they're talking with members of the community as well, and hopefully building some of that communication experience as well. So I'll leave it there with a thank you to all my students for all the amazing work that they did, and thank you all for listening.
Thank you so much, Stacy. It's super cool to hear about how you got all your students involved in collecting all this data around the city, and everyone in the chat is like super amazed. I guess one thing I wanted to ask about is we've been talking a lot about like graduate students throughout this live stream because many of our speakers are graduate students, but you're working with a lot of undergrads who are interested in meteorology. So I guess I'm wondering if you can speak to how like the recent like funding cuts and situation at like the National Weather Service is affecting their like how they're feeling about pursuing a career in meteorology. Like, are you noticing that they're thinking about these things?
Yeah, so I would say this summer, I think, was a real reckoning for some of the students. A lot of them had internships lined up with federal agencies, and some of them were with not necessarily National Weather Service, but the Forest Service or some of the national parks. And a lot of students had those unfortunately canceled. I had students who were applying for the NSF Graduate Research Fellowship, wanting to go to graduate school and facing those same issues of, those panels being canceled and the students just feeling like, what is going on right now? Maybe this is, not the time for me. Maybe I should just, work at Panera for a little bit and earn some money. So it's been really devastating in that sense.
Thank you so much for sharing it. For those in chat who don't know, the National Science Foundation has this like annual graduate research fellowship program that supports many graduate students, myself included. And this year, they cut the number of recipients down by half, which is a huge number of awards. Okay, so let's end with a science question from Astra H. How does this change on coastal cities, so the urban heat island effect, or even just generally urban meteorology if we're thinking about oceans, lakes?
Yeah, well, so that water is going to modulate the temperature difference quite a bit, right? Water takes a lot of energy to change the temperature. So we tend to see, our oceans or large lake systems, they'll stay a little bit warmer in the winter and they'll stay a little bit cooler in the summer. So they have sort of a tempering effect. So I would imagine coastal cities have sort of less of an urban heat island impact because of that water sort of modulating the system a little bit. You also have, sea breezes that are going to build up, mix that air really well. So when you have windy conditions, you tend to see less of an urban heat island impact because you're mixing all of what would be sort of that warm hot pocket that I said before with those cooler areas. You're mixing all of that up and kind of modulating it. So coastal cities probably don't deal as much with the urban heat island. That was a great question.
Thanks for the great explanation. Okay, it seems like we have time for one last question. I wanted to also highlight this environmental justice angle that you brought up. And like you were talking about how zoning policies like lead to these inequities in where there's like more of an urban heat island effect. But then you kind of hinted at this that like the green spaces where they're located, where these like mitigation things are located, is also um, very like segregated. And I think like another part of that is that these wealthier areas are also where people already have the resources to like have air conditioning and deal with extreme heat. So can you talk a little bit about like it's almost like it cascades, right? Like there are these feedbacks.
Yeah, absolutely. And I would say if I didn't make the connection there, I mean, part of the reason that we see less green space in these areas is due to that historic redlining. Because of that, you had sort of lower property taxes that would go to improvements, that would go to improving the road systems, that would go to, improving green spaces that are there, investing in parks. You just have, less money all around to do that. So that is why we see some of that disparity there. And it does feed back onto the temperature. It does feed back onto the air quality, right? And it just sort of perpetuates those issues as well. So it is certainly sort of a cascading impact there. But, I think people tend to think like, oh, well, that was a policy 100 years ago, right? We don't do that anymore. But the scars still remain. And that's something we have to reconcile.
Super important message to share. Yeah, everyone, thanks Stacy again for taking the time to speak with us. And I will move on to introducing our next guest. Thanks, Stacy. Okay, next I am super excited to introduce Dr. Allison Wing, who is a absolute superstar professor at Florida State University, and she is an expert on hurricanes and tropical meteorology. She'll be telling us about acceleration of hurricane development.
All right, good morning, everyone. Thank you very much for the introduction. It's a pleasure to be here and speak with you this morning. So yeah, as Lily said, I'm going to talk a little bit about some of the recent work in my research group on acceleration of hurricane development by cloud-radiative interactions. But first, I want to give a little bit of a background about overall what type of research we do in my group at FSU. So we study the organization and clustering of tropical clouds and storms, or tropical convection, and consider its implications for climate as well as hurricane development. And so since receiving my PhD in 2014, this research has been supported by a variety of different agencies, including the National Science Foundation, NOAA, and NASA. And in addition to supporting the actual research, including the results that I'll share with you today, this federal funding has also supported the education and training of 10 graduate students and 2 postdoctoral scientists in my research group over the last 11 years. And so that support has been really critical for building the careers of all of those people as well. So how do we actually do research in this field? As I'm an atmospheric scientist, and as I said, studying tropical clouds and hurricanes. So most of the time we're working at our computers, okay? And so this is either analyzing data from observations that have been collected either by satellites or in situ observations. analyzing output from big model simulations or running our own model simulations and analyzing that output. Regardless of what it is, it's a lot of data analysis using a variety of different tools. And so most of the time we're sitting at our computers, and I would say overall our group at FSU primarily really is a modeling group. That's most of what we do, is run our own model simulations of clouds and hurricanes, as well as analyze data from others. But occasionally we do actually get to go out into the field to collect our own measurements as well, including measurements of tropical clouds and storms. And so this is just showing me on a couple of recent field campaigns that I participated in, including this past summer on the Orchestra Piccolo campaign, but I've also flown on the NOAA Hurricane Hunter aircraft, as well as NSF NCAR's Gulfstream jet. And my research group has participated in this as well. And I wanted to emphasize that even as someone who's primarily a modeler, it's super important to incorporate observations in our research and to collect these observations. And part of the reason that we need to go out into the field to collect some of this data is that given what we're studying, tropical clouds and storms, we have to actually go there into the middle of the tropical ocean to collect that data. You know, there's not a lot of land in the tropics where you can have permanent weather stations. And so having research vessels and aircraft allow us to get to places that we can't ordinarily get to. And this enables measurements of the tropical areas of the ocean that are very remote. And so, for example, this movie on the right shows us launching a radiosonde from a recent research cruise in the tropical Atlantic. And these are weather balloons that collect profiles of temperature, humidity, and winds, and provide critical data for understanding the behavior of the tropical atmosphere. These sorts of aircraft also allow us to go chase certain targets, including hurricanes, and help us collect data from inside hurricanes. For example, using dropsonde instruments here, which are kind of like weather balloons, but they go down instead of up, collecting information on the temperature, humidity, winds as they do, as well as lots of other instruments on that aircraft. And that data is critical both for our research and understanding of hurricanes, but also for forecasting, because it gives us the most detailed information about what the hurricane looks like at that point in time, what its structure is, what its intensity is. And that data is really critical for both feeding into our forecast models and giving information to our forecasters to help us make the best forecast. And there's really no substitute for actually going out there and collecting the data in the storm. Okay, so that's a little bit about some of the different tools that we use. Now I want to talk about some of the science that we've been doing with that. And before I talk about hurricanes specifically, I want to take a step back and just think about tropical clouds and thunderstorms more generally. And so this is a photo I took during the OTREC, NSF-funded OTREC field campaign in August of 2019. And so sometimes this is what it looks like in the tropics. You'll have sort of a big, deep, tall thunderstorm cloud that sort of rises all the way to the tropopause and is surrounded by sort of calm, clear blue skies. And this is what it looks like sometimes, these sort of isolated or scattered thunderstorms. But that's not always what it looks like. And in fact, often our clouds and thunderstorms in the tropics are instead clustered together into organized systems. And so this is known as a mesoscale convective systems. You have multiple kind of individual thunderstorms together in this clump that then have this big sort of connecting cloud shield at the top. And they're tied together by a system scale circulation. And so this is really ubiquitous in the tropics. Again, sometimes it looks like this, but more often you actually see this clustering or organization. And so if we think about all of the different ways that clouds and convection and thunderstorms can organize in the tropics, they do so across a variety of different spatial temporal scales. And so this includes mesoscale features, like I mentioned, which are sort of around that 100 kilometers, which is 62 miles in scale. And this includes features like squall lines and these mesoscale convective systems. And these occur over both ocean and land in the tropics as well as in the mid-latitudes. And for those of us that live in the United States, these are the types of systems that usually bring us our severe weather, especially over the central US in the spring and summer, including things like strong thunderstorms, strong winds, hail, tornadoes, etc. And so it's really critical to understand what drives this sort of organization of convection and how it might change in a future climate. We also can have convection organized in the tropics on larger scales, though, on so-called synoptic scales, which is around 1,000 kilometers or 620 miles in size. And this includes tropical cyclones or hurricanes. And this is an example, I believe this is Hurricane Michael shown here. We also have what's known as equatorial waves in the tropics, and these are dynamical disturbances that are coupled with clouds and convection that really shape a lot of the day-to-day weather variability in the tropics. And so this is an example of an African easterly wave, which again brings its own sort of weather, but also can serve as a precursor for a hurricane. And then we can go to an even larger scale, the planetary scale, or around 10,000 kilometers, or around 6,000 plus miles, which includes features like the Madden-Julian oscillation, which is this blob of moisture and clouds and rain that sort of forms over the Indian Ocean and slowly propagates eastward across the Pacific. Or we can think of the intertropical convergence zone itself as a planetary scale organized convective system. And this is this undulating band of thunderstorms near the equator. So we have all of these different types of clustering or organization on a variety of different scales, and they're driven by a variety of different mechanisms. And these mechanisms include vertical wind shear. And so what vertical wind shear means is changes in the winds with altitude or height in the atmosphere. And we know that the interaction between vertical wind shear and the storms is really important for driving squall lines. This is an example from a radar image over the United States. On larger scales, convection and clouds and rain can also be organized by variability, spatial variability in the ocean temperature. So clouds and precipitation and deep convection tend to form where the sea surface temperatures are the warmest. And then you can get these kind of circulations between the warm and cool regions. As I mentioned before, we have this whole spectrum of dynamical disturbances in the tropics that then can provide large-scale forcing for organization of convection. And then we also can have sort of internal feedback mechanisms, such as cloud-radiative feedbacks. And that's what I'm going to focus on in the remainder of my presentation today. And we'll kind of walk through what this little cartoon schematic is showing. So what do I mean by cloud-radiative feedbacks? What does that have to do with anything here? So I think it's useful to kind of think about what the flow of energy looks like through Earth's atmosphere. So any object that has a temperature is emitting thermal or thermal radiation. And the amount that it emits depends on the temperature. And so at the temperatures that Earth is at, it emits radiation in the infrared. The sun does this too. It's just emitting at a much shorter wavelength because the sun is so much hotter than the Earth. And so this is the main way that Earth cools itself. So Earth's surface and atmosphere cool by emitting this thermal or infrared radiation upwards and eventually out of the Earth system into outer space. And so this is always happening. And we can think about then, how does that change? How does that flow of energy through the atmosphere change when we put a cloud there? So if we have clouds now, clouds as well as moisture in the atmosphere affect this flow of thermal radiation. In particular, they're really good at absorbing it, and then they can re-emit it back up at their temperature. Now, clouds also can reflect sunlight, which is another big effect that they have on radiative energy in the atmosphere, but I'm not talking about that effect here. I'm talking about just how they affect the thermal radiation that Earth is emitting. Now, if you have low clouds, like in this image here, you'll get this really strong cooling of them at their tops, but it doesn't really change what goes out to space that much because these low clouds are low in the atmosphere and they're at a similar temperature to Earth's surface. But instead, if we have a really thick, deep, tall cloud like associated with a thunderstorm, these have a big impact on what happens to this flow of energy. In particular, they are able to trap a lot of that heat in the atmosphere as this kind of cloudy greenhouse effect. So what happens is that the surface is emitting this radiation. That gets absorbed by all of these sort of, lots of sort of heavily laden water droplets or even ice crystals in the top of the cloud. All this water in the cloud is really effective at absorbing that radiation and providing local warming of this region inside the cloud. Then at the top of that cloud, you have really strong cooling to space. But because these cloud tops are really, really high up in the atmosphere, like, many miles up, kind of around where airplanes fly, they're much colder than at the surface. And that means they are emitting less infrared radiation to space. And so when you have a thick, deep cloud like this, it's trapping heat in the atmosphere, and less is actually escaping to the atmosphere out of space, causing relative warming of the atmosphere below. And so if we think about what's happening in the atmosphere in a region where we have lots of thick, deep clouds like this with lots of water in them, compared to the more clear sky areas, we tend to have anomalously more warming of the atmosphere in the cloudy region and more cooling of the atmosphere in this clear sky region. This means that we can kind of set up a feedback process where this difference in where we have radiative heating and cooling in the atmosphere affects the propensity for convection in those different regions and can also set up circulations. So these images were actually taken, they're not next to each other in reality. I took these at 3 separate times, but just kind of put them side by side to show you the different processes. But if we think about a single system, we have a similar picture here. And so this is probably one of my favorite photographs I've ever taken of a mesoscale convective system, this big clump of thunderstorms over the tropical East Pacific Ocean. And where we have all of these thick, deep, super, wet clouds, here they're going to be cooling from their tops, but we're going to have, relatively speaking, more warming of the atmosphere inside the cloud in the lower to mid troposphere, compared to these outer regions here where there's less clouds, and so there'll be, relatively speaking, more cooling. In the atmosphere, anytime you have differences spatially in how much heating or cooling of the air there is, this sets up a circulation of air between them because it's trying to even out that difference. And so we tend to then have rising motion where we have this extra warming. And that air needs to be replaced then by air flowing in from the drier region to the periphery. So you get this sort of overturning circulation that's favoring rising motion in the cloud, which is the same place where we already have this strong rising motion in those thunderstorms. And so that's a positive feedback that helps these clouds clump together and cluster into organized systems. So that's just in general how these cloud radiative interactions work and help convection cluster together. How do we apply this to tropical cyclones specifically? Well, this is an animation of Hurricane Helene from this past fall, which made landfall in Florida and then went on to dump a huge amount of rain over the Carolinas and Tennessee and Western Virginia. And if we look at the cloud shield here versus a satellite animation, so we're looking down on the top of the storm. Around the center of the hurricane is where we have all of this thick, deep cloud cover. And so that's going to have more warming in the atmosphere relative to the clear sky areas on the periphery of the storm. And so in our group, we're investigating this sort of variability in the radiative heating and cooling in a hurricane and thinking about how that affects the development of the hurricane itself. And we're doing that using a variety of different tools. So we're investigating how these cloud radiative interactions affect hurricane development by using NASA satellite observations from primarily the satellite CloudSat, which is no longer flying, but it did for a large number of years until a couple of years ago. And then we're also using in situ data from the NOAA Hurricane Hunter aircraft. And in addition to this observational data, we're also running high resolution computer model simulations of imaginary hurricanes using NSF NCAR's supercomputer Duratio. And so what do we learn from doing these different simulations? So one of the really nice things about running a model simulation of any sort of weather or climate phenomena is that we can go in and change processes in the model and turn different processes on and off and see what effect they have on the simulation. So that's what we did in these model simulations. We're just simulating a hurricane in a box, and we're not simulating any particular storm from the real world. We're just generating an imaginary hurricane by starting with this little warm, moist bubble in the middle of the domain and letting it adjust to that and do what it wants. And I'm going to show you an animation looking at 2 different simulations here. The one on the left is the normal or control simulation, where everything is happening, at once, and we turn all of the different physical processes on. The radiative heating and cooling is calculated interactively using the simulated clouds and moisture. But in the simulation on the right, we've turned off those cloud radiative interactions so that there's no variability spatially in how much radiative heating cooling there is. Even if there might be more clouds in one place, the model doesn't know about that from the perspective of the radiation. So in this animation here, the colors are showing wind speed near the surface. So if I play the animation, we'll see that we have this initial adjustment to this bubble that we initialized with, and then we get this sort of broad, weak circulation to form in both simulations. In the normal simulation on the left, the wind speed quickly increases and that broad circulation contracts into a strong tropical cyclone. It's already like a category 4 storm at this point. Whereas in the simulation on the right, where we've removed these cloud-radiative interactions, for a while, nothing really happened. Eventually, after 8 or 9 days of the simulation, we do get a hurricane to form. But if I play that again, you'll see that it takes much, much longer for that circulation to contract and intensify into a hurricane when we don't have these cloud-radiative interactions. A hurricane does still form eventually, and so these cloud-radiative interactions aren't strictly necessary for the hurricane to form, but they sure help it form a lot more quickly than if we don't have them. And we can see this even more explicitly by looking at the time evolution of the wind speed in these simulations near the surface. And so I haven't put the numbers on the axis, but basically on the y-axis, as we go up, we have stronger winds at the surface, and then the simulation time is progressing on the x-axis. The black lines are our normal simulation that has all of these cloud feedback processes in them. And then the gray dashed line is our simulation where we've turned off these cloud-radiative interactions. This line is about tropical storm force wind. So that's when we would name the hurricane if it was happening in reality as a tropical storm. And we can see that there's a big difference in how long it takes these two sets of simulations to make it to that point, where our control normal simulation takes a little over 3 days for the hurricane to develop. But in our simulation without these cloud-radiative interactions, it takes about twice as long, a little more than 6 days for the hurricane to form. And that's a really big difference. We can also kind of look at the differences in structures at a given time during the simulation. So if I choose day 5, for example, at that point, we have a mature, intense, it's a category 5 hurricane at that stage in the normal simulation. And it looks like this. We have an eye, we have lots of sort of deep, tall convective clouds and this very highly organized circulation. However, at the same time, in our simulation without the cloud-radiative interactions, we have a much weaker system with very weak winds, less intense, less deep convection that's sort of scattered about, and it just hasn't really gotten its act together. And so this really clearly shows the impact that turning on these cloud-radiative feedbacks has on helping the hurricane form much, much more quickly. Now, this is in model world, in particular idealized model world, right? I was simulating a hurricane from a bubble in a box, not super realistic. It's nice because we could play around with things and really understand things. We've done other simulations as well, where we have simulated real hurricanes, including past intense hurricanes like Hurricane Maria and Typhoon Haiyan. And we see a very similar behavior if we turn off these cloud-radiative interactions in those real case study simulations. It also either delays or even prevents the hurricane development. But we'd like to verify that these processes are happening in the real world as well. And so that's where we turn to our satellite observations. So this is an example from the CloudSat satellite of an overpass through a typhoon. And this is basically like taking an X-ray through the middle of the storm and telling us its inner structure. So the colors here are reflectivity from the radar, which is basically telling us where all the clouds and rain are. And then I've overlaid some arrows to kind of give you a sense, of the hurricane circulation. So remember, as in a hurricane, we have air flowing inwards towards the center of the storm at the bottom, spiraling around in the northern hemisphere counterclockwise before rising up near the center in the eye wall, which is where our most intense thunderstorms are, and then flowing outwards at the top of the storm before sinking in the environment. And so if I overlay my little cartoon view of the clouds and radiative heating in this hurricane on top of this, we have most of our deep clouds kind of confined near the center of the storm. And so we'll have lots of warming of the atmosphere below those cloud tops compared to these outer regions where we'll have relatively less warming or more cooling. And that structure of the clouds is shaped by the hurricane circulation, And then, as I talked about before, those differences in the radiative heating can feed back on the development of the storm and its circulations. And indeed, that's what we find. And so we took all of these overpasses through different hurricanes and typhoons around the world, took the satellite estimates of the cloud properties and calculated what the radiative heating of the atmosphere would be given that. And that's what's shown in the color shading here. These are anomalies from a mean over the whole storm. So it's saying where it's warming or cooling more than average. And this plot is showing that as a function of height going up in the atmosphere and radius from the center of the storm working our way outwards. And so again, we see that we have all of this sort of warming of the atmosphere below our cloud tops, which are about here, and cooling above. The contours are showing the circulation that's driven by these differences in radiative heating. And so we get this in, up, out circulation that helps drive rising motion in the core of the tropical cyclone, moistening the atmosphere there to make it easier for the hurricane to spin up and develop. The other thing that we find is that not only does this sort of cloud greenhouse effect accelerate the formation time or make it easier for the hurricane to form, it also is stronger for storms that undergo rapid intensification. And so rapid intensification is when a hurricane's intensity, its winds, increase by more than 30 knots in 24 hours. And in our computer model simulations, we have a metric that allows us to denote the strength of this TC infrared radiation feedback. And we compare that to how quickly the storm is intensifying in that simulation. And we find that across all of our simulations, the cases with a stronger cloud radiation feedback have a faster intensification rate. And in particular, if we compare the storms that are rapidly intensifying versus the ones that are less quickly intensifying, you basically need to have a strong cloud radiation feedback in order to get this rapid intensification. And that's seen in the satellite data as well, where we have the same metric of our feedback strength. And now we're plotting it as a function of radius from the center of the storm going outwards. And we've composited that over cases of storms. We look at thousands and thousands of overpasses over lots of hurricanes over many years. And we split it into ones in red that are rapidly intensifying. And then the other colors show storms that are intensifying more slowly. And again, we see that in the rapidly intensifying storms, we have this stronger feedback. So the idea here is that if the sort of structure of the clouds is in a way such to give us a bigger cloud radiation feedback on the hurricane, then that makes it more favorable for the hurricane to intensify further and more likely to undergo rapid intensification. So the last thing that I want to mention is why this is important. And this is important because rapidly intensifying hurricanes are very dangerous, especially when they undergo rapid intensification right before landfall. Imagine going to bed thinking that you're going to have a Category 2 hurricane affect you, and then you wake up and it's actually a Category 4 instead. You don't have any time to prepare, and you have a much more dangerous storm. It's also very difficult to forecast them. So this is showing the National Hurricane Center's errors in their intensity forecasts as a function of lead time over different decades. And these forecasts have been really stubborn for a long time until the last 15 years or so, when due to a big investment of effort and resources from across NOAA and other agencies and universities, they really have improved their forecasts a lot. But rapid intensification is still really difficult. And so the chart on the right is showing the probability of detecting rapid intensification in these different forecasts. And that's increasing with time, which is good. Our forecasts are improving, but we're still only detecting maybe 20% of those cases. And so we really need to do everything we can to improve these forecasts. And so one of the other things that we're doing in my group is developing diagnostics for these cloud radiative feedbacks and other processes to evaluate them in models to help us improve our model simulation of hurricanes, as well as the hurricane precursor disturbances. So this is the global view of what hurricanes look like around the world. And here's what one climate model shows. Pretty good, right? It's kind of putting the hurricanes in the right place. And so our modeling capabilities, both for forecasting individual storms as well as the sort of climate simulation of hurricanes, has really improved a lot. But if I show a different model, it's not always as good. And so there's still a lot of biases, and our diagnostics can help us identify what parts of the model to target to improve our simulations. And we actually had a proposal to apply these diagnostics to hurricane precursor disturbances in NASA model forecasts, which was selected for funding, but we don't know when or if it will ever actually get funded. And so we don't know when or whether we'll be able to do that research. So with that, I'll end, and hopefully I've conveyed the message that these cloud-radiative interactions are important for hurricane development, which means that understanding and correctly simulating them is important for both improving our understanding as well as forecasting. Thanks very much.
Thank you so much, Ali, for that super interesting talk. As a reminder to all our viewers, part of the reason we chose to do this 100-hour live stream is that hurricane season officially starts this Sunday. So super nice to have some talks about hurricanes. We have a really great question from Kat, which is, in your research, how much data would you say is from models and how much is from observations? And like, is this something that's like typically normal for meteorology research?
Yeah, so in my research, we definitely do more work with models than directly with observations, but both are really important. Ultimately, we're trying to understand the real world, and so we have to understand what's happening in observations, and those observations are critical for validating what our models are doing. The models are useful because, as I mentioned, you can go in and sort of change things in the model. I can't go out into the real world and make the clouds invisible, but I can do that in a model. And so using a combination of observations and modeling really is the best combination for gaining understanding. And so exactly what the balance is varies from person to person, and it varies also depending on the topic that you're studying. But throughout my career, I started as a modeler, and with time, I'm working more and more with observations, and I really love using both tools.
Yeah, that's a great point about the constraints that we have to work with as meteorologists and climate scientists when we're trying to perform experiments on like the Earth system. I have one last question, which is, just now in your talk, you described a way that hurricanes interact with their environments to intensify them, but are there other ways that hurricanes interact with their environment that lead to their destruction?
Yeah, absolutely. So there's lots of different aspects of the environment that affect tropical cyclones, so in hurricanes. So at the basic level, you need warm ocean temperatures, a moist atmosphere, some spin in the atmosphere in order for the hurricane to form. One thing that I mentioned can help convection organize is this vertical wind shear when the winds are varying with height. But that is actually bad for hurricanes. And so if you have really big changes in your winds with height in the atmosphere, that can import dry air into the middle of the hurricane and kind of kill it and shear it out and either prevent it from forming or make it harder for it to intensify. And a big area of research right now is actually studying the intensification and development in storms that have sort of medium levels of that vertical wind shear, because then it sort of depends on other environmental characteristics, like how moist the environment is, whether that's sufficient to prevent the storm from developing or if it can still intensify even in the face of that vertical wind shear. And then, of course, as hurricanes also move over colder waters, that will slow their intensification or help them weaken. And so you have all of these things going on together at the same time. And some processes will be trying to push the hurricane to develop and intensify more quickly. Some processes will be trying to hold it back. And what actually happens is a delicate balance between all of these different things.
Great. Thank you so much for sharing your expertise with us. Everyone say thank you to Ali in the chat and let us know if you have any more questions. We'll read through them. Thank you. Okay. We are now in the 20th hour of our weather and climate live stream. So before I introduce our next guest, I'm going to say a brief reminder of what this live stream is about. We are a bunch of meteorologists and climate scientists who are trying to save America's forecasts. What I mean by that is that we think that all Americans deserve good weather and climate forecasts, and US scientists have been at the forefront of weather and climate predictions for a long time now. So, American scientists developed the first computerized weather forecast. We ran the first computer climate models, modeling CO2 warming, and we also just have this really amazing, truly unparalleled network of observations that Ali just highlighted, and it's made possible by decades of federal investment. And so that is to say, it's all thanks to you, the American public, for our American viewers. I know there's a bunch of friends joining us from abroad as well. And what we're trying to communicate is that like US funding for science has really been so critical to saving lives, but there are these ongoing funding cuts that are affecting all areas of weather and climate science. And yesterday we had a panel of former NOAA employees who were telling us about how much they just really care about the work that they're doing, and how since being terminated, that's really affecting the ability of their former teams to be able to issue these forecasts and warnings in a timely manner. So we're hosting this 100-hour streamathon to spread the word about weather and climate science. And if you'd like to help us out, please share this live stream with your friends and family, and also tell them what you're learning about weather and climate science. Like, I think one really great thing about the stream and like our interactions with all of you is that it's just been this like really lovely celebration of science, and like we're so happy that you guys like learning about our science and our very like niche research interests. So yeah, if you're inspired to help us out and like help out American Forecasts, like please talk to your friends, family, and representatives. And if you don't know how to do that, we have made it very easy for you. There's this link you can visit, wclivestream.com/act. You just put in your zip code, and then we have a script ready for you and a list of your representatives' phone numbers. So thank you so much, everyone, for tuning in. And now I'm going to introduce our next speaker, Dr. Kirsten Findell. She is a research scientist at a government lab, and I don't know how many of you were here for my land versus ocean debate earlier, but Kirsten is like the queen of land-atmosphere interactions, so we're so fortunate to have her here with us today. Take it away, Kirsten.
Well, you're very, very kind, Lily. Thank you for that introduction, and I'm excited to be a part of this. Thanks to all of you who are creating the opportunity for us to share some of the work that we do, some of the research that we do. So yes, I want to talk about land, and I want to talk about land-atmosphere interactions, which has been the heart of my work for many years now. But of course, I have to start with the sun, because the sun is the main driver of the weather and climate system on Earth. That's where our main energy source comes from. And then that sun's radiation, of course, passes through the atmosphere. And we've heard many other speakers attest to the importance of the atmosphere's role and the greenhouse effect, and how important that is for making our planet the wonderful habitable environment that we have. And of course, many other speakers have touched on the ocean and how important the ocean currents are for distributing the heat that the ocean absorbs and distributing that around the whole system. But I'm going to focus on land today. I'm going to focus on land and land-atmosphere interactions. And we see this beautiful satellite image of NDVI, which is the Normalized Difference Vegetation Index. So it's a satellite-based index that shows us something about the greenness on Earth. And why is that important? Why is it important? Well, it's important because there's a huge diversity of what the surface of the Earth looks like when you're looking from the atmosphere perspective, right? You can have a tropical forest in one region and a dry, arid landscape in another. But you can also have diversity in time for one given location. And here's an example of the Oroville Dam in California that went from, in 2017, when the reservoir was nice and full. That was after a years-long drought, which you can see in 2014, that the whole reservoir was almost completely empty. So you can have a lot of diversity on land, both in space and in time. And why is that important? Well, that's important because the land surface and the vegetation at the land surface and the moisture availability at the land surface play a big role in determining the response of the atmospheric boundary layer. So the boundary layer is that layer of the atmosphere that's influenced by surface fluxes, or fluxes of heat and energy and moisture and momentum from the land surface. So over these two sort of very different landscapes, you see that there's very different surface characteristics, and that leads to very different atmospheric boundary layer characteristics. Over on the right, we have this nice lush forest where there's lots of moisture available. So when sun's energy comes in and hits that surface, most of that energy is going to be consumed by evaporation and transpiration, right? The plants are going to pump moisture through their system, through their stomata, and most of the energy is going to be consumed by evapotranspiration. There's very little that's going to go into sensible heat flux. Whereas if you go over to the picture on the left side, where there's just very little moisture available, almost all of the energy is going to go into just sensible heat flux, which is really heating up the air, right? And we know that hot air rises, so there's going to be a lot of lifting mechanism from that high sensible heat flux that's going to lead to hot, dry, and deep boundary layer. Whereas over on the wet side, on the highly vegetated side, the boundary layer is going to be much more shallow, but you're going to pack a lot of moisture into that shallow boundary layer. So there's actually a lot of energy in that boundary layer, energy in the form of water vapor. And that has huge implications then for the possibility of triggering convection, right? So one of the things I did early on in my career during my PhD work, which I was fortunate enough to have my PhD supported by an NSF graduate fellowship when I was working at MIT. So very grateful for that NSF funding. That funding allowed me to follow the science, right? To follow the science and follow where it took me. And it allowed me to create this framework that I called the CTP-HI-low framework. So CTP stands for convective triggering potential. And then the HI-low was a low level index of the humidity deficit. And through this framework, as I was able to demonstrate that there are different ways of the land surface and the boundary layer growth influencing convective triggering. One can be that when you have that high sensible heat flux, the boundary layer is growing up until it reaches what we call the level of free convection, where there's buoyancy and clouds and potentially rainfall can occur. But on the other side, you can increase that boundary layer moist static energy so much that you effectively bring that level of free convection down. And so it's two entirely different mechanisms. And we were able to demonstrate where and when each of those mechanisms were important. But that sort of column view of these processes, that sort of 1D perspective on land-atmosphere interactions, was an important sort of formative way of looking at land-atmosphere interactions in my early career. And there are a lot of other people who look at it in that same 1D perspective. And many of us have collaborated for years and come together to talk through this LOCO coupling group, the local land-atmosphere coupling that we just call LOCO. And this is important because it allowed us to come together as scientists who are looking at similar problems and give us a forum for sharing our work and really probing deep into the mechanistic processes that were of interest to all of us. But this was also in a larger context. The LOCO coupling project is part of GLASS, the Global Land Atmosphere System Studies, which is a panel that's part of GWEX, which is a project that looks at the global energy and water cycles. And GWEX is a part of WCRP, which is the World Climate Research Program. So I'm sharing this acronym soup just to say, these are all scientific communities, right? And science advances most when we can come together in these different communities and share our work, probe each other's works, ask each other's questions. And sometimes it's helpful to have that come together as community where we're working on similar projects. Sometimes it's helpful to come together as interdisciplinary scientists. And sometimes it's helpful to share it with audiences more widely. But all of these different mechanisms for sharing and working together give us the opportunity to really have those aha moments where the science moves in leaps and bounds. So I want to thank all of these institutions for creating those opportunities for coming together to discuss our science. So what did we learn in that LOCO environment? Well, I think that local perspective has taught us a lot. I've already shared that boundary layer growth depends on surface flux partitioning. We learned that triggering of convection depends on the stability and humidity above the boundary layer. We were able to show when and where the land surface has the potential to influence convection and which mechanism is more efficient for triggering convection in different circumstances. Also later able to show that flux partitioning at the land surface influences the triggering of convection, but not the amount of rain that falls, that the amount of rain that falls is more determined by the amount of water vapor that's already in the atmospheric column above it. We're also able to apply that perspective to questions of how vegetation modulates surface fluxes and thus near surface conditions. So this is a map it's a difference plot from many years, from two different sets of simulations with an Earth system model. One of those sets of simulations is our best estimate of the historical world as we know it. And the other set, we call the potential vegetation simulation, is like the historical, except there's one thing changed. And that's that our trajectory of the land, the depiction of the land, instead of in the historical simulation, we have the depiction of land use and land cover change as it happened with humans altering the land surface over the last couple hundred years. But in the potential vegetation scenario, we just say, well, what would the vegetation on all over the Earth look like if humans hadn't altered it at all? So by doing that, essentially we're looking at, in a sense, a deforestation scenario in places where humans have changed the landscape a lot. And what we see in these two red regions is that with less forest cover, summertime means are both hotter and drier. So that's the depiction of the mean, but we can also look at extremes, and we can also look at, well, what happens to the frequency of hot, dry summers? And what we were able to conclude from this work was that in these regions with red on the maps, what would have been a once in a decade hot, dry summer in that potential vegetation world actually occurs every 2 to 3 years in these historical simulations. So changes to the land surface do influence both the means and the extremes of what we experience in our near surface environment. So that brings us to the question of why don't extremes change in the same way as the mean? And there's many reasons for that, but one of the key reasons is this nonlinear relationship between soil moisture and evapotranspiration. So this is something that, here's a schematic plot of it. If you can see my mouse, yes, I think you can. On the x-axis, I'm showing soil moisture. On the y-axis, I've called it latent heat flux. You can think of that as the same as evapotranspiration. You can see that when soil moisture is very, very dry, essentially there's just not enough moisture to have any real latent heat flux. But if you add a little bit more soil moisture, at some point you get into this transitional regime where more soil moisture directly means more latent heat flux. But at some point, you can add enough soil moisture that soil moisture is no longer the limiting factor. There's enough moisture around. It's energy that's the limiting factor. So this distinction between water limitation and energy limitation is really, really important. But it's not just that sort of functional relationship between those two variables, which I'm depicting again on the top side here, on the top right here. It's also the distribution of soil moisture at any given location. How often you have days that are in each of these different regimes is a really important factor. So when you think about, say, a warming world, that might shift your soil moisture PDF, the probability distribution function, the implications of that soil moisture shift for evapotranspiration are really dependent on where the shift occurs according to these different regimes. If the shift occurs in this wet regime, you can get drier in this wet regime, but it's not going to change the evapotranspiration. But if you go from, having many, many days in the wet regime and those get drier so that they move into the transitional regime, you're going to start to have limitations to your evapotranspiration. And then that's going to have implications for other surface variables. And we can see this when we use this phase space that was developed with work that postdoc Suchin Duan did not too long ago. This was the soil moisture aridity index phase space. And it's a really helpful model, a helpful space for understanding this physical system in its mechanistic, from a sort of physics and mechanistic view. So here over on the right, I have a map view of the tropics where I've calculated an aridity index and then sorted it according to percentiles. So the most arid regions are these desert regions, the most humid regions like the rainforests are here in green. we've sorted those grid points along the y-axis here. So we can think of the y-axis as space, with the most arid regions across the top and the most humid regions across the bottom. The x-axis is daily soil moisture sorted into percentiles. So it's effectively like a PDF that I showed you, that PDF of soil moisture that I showed you from the last time. So what this space allows us to do is look at differences. And here again, I'm using differences of a 4 times CO2 experiment. So this is a much, much warmer world compared to a pre-industrial experiment. And we can see that the middle plot is delta soil moisture, so change in soil moisture. And you can see that in that much warmer world, soil moisture dries almost all of at all locations, at all y-axis, we can think of locations, and on almost all days. So we think of the x-axis as days. But even though soil moisture is drying all the time, latent heat flux is not decreasing all the time. In some places it increases, and that's a direct result of this nonlinear relationship. So we can actually map those regimes of this nonlinear relationship onto that delta latent heat flux plot. And it tells us a lot about the vulnerability, the amount of time and space that will be vulnerable to, say, prolonged droughts and increased incidence of heat waves. And why do I say heat waves? Well, because there's a clear temperature response when you think about this redistribution of that change in the surface flux partition, that change in the use of radiant energy. So here we have the soil moisture and the latent heat flux deltas that I showed you on the last slide. And over on the right, this is daily maximum temperature. So you can see that daily maximum temperature it's always positive, right? This is a 4 times CO2 minus pre-industrial. So it's a much warmer world. It's warming all of the time and space in this depiction, but it's warming more in these red regions. And there's 2 zones of those red regions. The one across that the top swath is all days in the very arid regions. So that's telling us that there's a shift of the PDF. So that probability distribution function of temperature, of daily maximum temperature, is shifting to warmer conditions. Now across the bottom, where we see that other red region, that's telling us that these days, the days that are the driest days are warming more than the days that are the wettest days. So that's telling us that in these moist and semi-moist regions, there's a shift towards warmer temperatures, but then there's also a lengthening of the warm tail. So the hottest days are getting hotter. So really important implications for heat waves and droughts. So let's look at heat waves and droughts. So this is now I'm pointing to some recent work that a different postdoc, Dong-Hyuk Yoon, is doing, where he's looking at severe heat waves from a regional perspective. And what he's done here is he's got 6 different heat waves happen that were really like globally important heat wave events in different parts of the world in recent years. And for every grid point from our model here, for every grid point, or from this observational data set rather, for every grid point, he's determined the day of the maximum temperature anomaly. And he's calling that day 0. So in these time series here, day 0 is in the middle. And we're also looking at the 15 days prior to it and the 15 days after that peak day, so that we can start to say something about how predictable are these heat waves and how predictable are the associated droughts. So we have droughts and heat waves. So the top is temperature, T maximum temperature anomalies, and the middle here is soil moisture anomalies. You can see the green line are the associated time series for soil moisture. The pink line are the associated time series for temperature. But what about latent heat flux, right? I've been talking about latent heat flux a lot up to here. And there we've added the time series for latent heat flux. And there's some interesting things happen. You can see that in some years, there's a really strong correlation between Tmax and latent heat flux. But in other years, there's a really strong correlation between soil moisture and latent heat flux, even though soil moisture and daily maximum temperature are anti-correlated, right? Those hottest days are often the driest days. So what's going on here? Why is Tmax, or why is latent heat flux sometimes strongly correlated with one variable and sometimes strongly correlated with the other? There's lots of work that Dong-Hyuk has done looking into this. This is a synthesizing figure. I can't go into all the details, but I'm going to orient you on this complicated figure because I think it's a really exciting one. So on the x-axis, this is that correlation between soil moisture and latent heat flux. So those years where soil moisture and latent heat flux are highly correlated is over on the far right. The y-axis is the correlation between temperature, Tmax, and latent heat flux. So those are on the top. And the colors are depicting evaporative fraction. So this gets at that surface flux partitioning that I was talking about right at the beginning. Where that evaporative fraction, this is essentially the amount of the available energy that's consumed by latent heat flux. So where the evaporative fraction is close to 1, that tells us this most of the energy is going into, is being consumed by evaporation. And those are conditions when the atmosphere is just demanding as much moisture as it can get from the land system. On the other side, with these red dots, that's where this severely water limited, not much of moisture is available for latent heat flux, so most of it is going into sensible heat flux. And that's where the dryness of the land is restricting latent heat flux and then driving the temperatures up. So, and the difference between these drivers for these compound drought heat wave events have really important implications for the predictability of these compound extremes. So speaking of extremes, this is the last thing I'm going to touch on here. I want to touch on 2023 because 2023 was a year of enormous extremes and surprising extremes in many ways. I remember hearing about, on the bottom there, I'm showing sea surface temperature. I remember hearing about, you know, the hot tub temperature waters surrounding Florida during much of the summer. I remember hearing about, you know, heat waves on every continent and droughts on every continent at some point during 2023. And of course, I remember the Canadian wildfires that raged across, you know, much of Canada throughout that summer. And another really memorable and surprising thing from 2023 was the September global surface air temperature anomaly, which you can see this is a time series of September's global surface air temperature anomalies going from 1940 out to 2023. You can see that normally the changes from one year to the next are you know, relatively modest, but that jump in for September of 2023 was just shocking. So some of us who are involved in various programs related to the World Climate Research Program decided that we, as a sort of interdisciplinary group of scientists, of earth scientists, should say something about this, should understand what's going on. So I co-chair one of the WCRP Lighthouse activities, the one called Explaining and Predicting Earth System Change, which is described in that 2023 paper. And there were 6 of us that came together we're you know, some are oceanographers, some are experts in radiation. We came together to look at what were the causal factors of these unprecedented extremes. And there were 2 primary things that I want to highlight. One was that there's a positive trend in Earth's energy imbalance. The amount of energy that the Earth system is taking in, here's net radiation in red. You can see that it's going up. And this is really alarming because that's just more energy for the Earth system to absorb, to take in, and to distribute. The other important thing that happened in 2023 was that there had been a 3-year-long La Nina and the switch to El Nino in 2023. Really, during the La Nina years, some of that incoming radiation was brought deep into the ocean or below the surface layers of the ocean. In 2023, with the switch to El Nino, that was brought back up to the surface, and there was nowhere else for it to go but the surface waters and the overlying atmosphere. So lots more I could say about that, but I want to end with just some closing thoughts, and that's that science is collaborative. You know, science is collaborative, it's multidisciplinary. It requires exploration, experimentation, hypothesis testing, coming together to discuss your work and probe each other's results. You don't always know where that exploration is going to lead, but as our understanding of the Earth system increases, so does our ability to adapt and to mitigate and to ameliorate and ultimately to become more resilient, which is what we need right now. So with that, I'll stop and thank you all for listening.
Thank you so much, Kirsten. We actually got so many questions for your talk. I'm going to start with a, let's say, local question. So we have someone who works for a Mesonet site, which is super awesome. And Jace asks, out of curiosity, how much is local Mesonet data used for some of this? Because they know that a lot of those instruments measure soil moisture.
Yeah, those measurements of soil moisture are really, really important because soil moisture is I'm just going to stop sharing here. Soil moisture is so heterogeneous in space that one soil moisture measurement is so important. And of course, we always want more, right? We always want more. But these mesonets, where people are actually taking observations and taking them over long periods of time, taking discrete observations over periods of time, are really, really important. As part of that glass panel that I mentioned, there's projects where we're taking observational data from mesonets, from FluxNet stations, from wherever we can get it, and trying to bring that together to use that to confront the models, to say, are the models doing a good job at representing the soil physics, at representing that surface flux partitioning that I talked so much about. So we can only know if our models are doing a good job if we have observations to compare them with. So thank you for being a part of whatever soil moisture measurements you do. It's really important for understanding the system.
That was a great reminder about the importance of observations. So now I'm going to switch to something that's maybe a little more non-local. And Arturo asked, does soil moisture change the length of monsoon precipitation? Are there any interactions there?
Yeah, that's really interesting. So oftentimes it's large-scale systems or maybe land-sea contrasts that might sort of set up the big picture. But some people have looked at that, say, the Indian monsoon, to say, does irrigation influence the timing of onset? And in some regions in the Indian monsoon region, you've seen that it can start maybe a week or two earlier because you have more moisture at the land surface through irrigation practices. It can also affect, there's lots of people doing work in West Africa, looking at how soil moisture gradients affect the onset of monsoon, the how long it lasts, when it finishes. And so there's lots of work going into this. The results are, I think, sometimes regionally specific because it's about the interaction between the large scale the circulation that's the regional scale circulation, I should say, and local soil moisture gradients and means.
Okay, well, I could talk about soil moisture literally the rest of the day, but we do have to say goodbye to Kirsten. So say thank you, Kirsten, everyone in the chat. It was so great having you. And
thank you so much. Pleasure to be here.
Bye-bye. And before we move on to our next speaker, we are almost at the, oh my God, 21st hour. It's almost 6 a.m. here. It's like right outside. So it's probably time for me to go to sleep, but not before we hear from our last speaker, Dr. Michela Biasutti, who's a Lamont Research Professor at Columbia University. And speaking of monsoons, we're going to hear a little bit more about them just now.
Yes, so thanks everybody. It's already 8:30 here in New York on a rainy day, and I'm gonna talk to you about rainfall, drought and floods in monsoon regions. I wanna start out though by telling you how I got here. And I started out as a physics major, and I got my degree in a public university in Italy. I got a fantastic public education in Italy. And then 1995, I'm done there, and there's nothing for me to apply all that training to. And the place to go, if you were a go-getter and you really were passionate about research, that was the United States. And so I moved by myself to Seattle. I went to the University of Washington. I got a couple of degrees there, including a PhD in atmospheric sciences in 2003. And then I made New York my home. I've been at Lamont, which is a branch of Columbia University, since 2004. So it's been a very good career here in the United States. I am now a citizen. I've raised my family here. I feel very strongly about the importance of keeping the US research as a beacon for the entire world. Okay, but my research interest, it's much easier to explain than back when I was doing particle physics. My research interest is rainfall and its impacts. And so here is a picture of just the rainfall in the monsoon in India. And so, first of all, let's think about all the good stuff that rainfall brings to us, right? We depend on it for everything. But of course, rainfall can also be destructive. And so over the course of these 20-year careers, I've looked at a lot of aspects of what rainfall does and can do. And so here is an example of a collaboration with NASA, when we looked at this amazing data set of landslides gathered from news reports and social media, and really trying to figure out if we could use this kind of very new data set to understand quantitatively the relationship between extreme events of rainfall and landslides, at least in places that are urban area where we have a lot of news coverage. So very interesting way of using all sorts of data in interdisciplinary ways to understand and possibly, help mitigate the effects of destructive rainfall. I've also done work on understanding what especially monsoon rainfall does to crop yields in places that can be very vulnerable to vagaries of rainfall. And again, important for global stability. What happens if there's a famine in a place like this? So, the very broad scale impacts of rainfall variability. My passion, it's understanding, though, the dynamics of how this event happened. So, for example, how do we get a deluge like the one that put Pakistan under water for most of the summer in 2022? Or at the other end of the spectrum, how do we get a drought like the one that was devastated the Sahel, the region just south of the Sahara Desert in Africa, in the 70s and in the 80s. Again, we'll come back to this episode. But let me start first with the very basic, although it's especially if you're logging in right now, this might be important. Otherwise, if you've been listening to Allison Wing earlier today, you already have a whole lot of knowledge about what makes rainfall, especially in the tropics. But here we go. So what is the recipe for rainfall? Well, if you're just to get a cloud, any kind of cloud, you need two things. Of course, you need the water, vapor, but you also need to bring that water vapor to a place in the atmosphere that is cold enough that water vapor will condense into cloud droplets. So here you see what is called the lifting condensation level, right? The cloud is flat at the bottom and then bubbles up on top of it. This level here is where it's cold enough for water to condense. And so you can make these tiny little clouds, but this won't rain. What do you need to get rain? Well, you need to grow this cloud to be a lot taller, a lot larger, and possibly long-lived, so that those tiny cloud droplets will actually grow, will coalesce, will collide, will form big drops of rain. And the bigger this system, the more rain you can get. So to get an extreme rainfall, you need the conditions to create something like this. So what gives you upward motion in the atmosphere? Well, it depends on there's four main mechanisms. you can get this, very small scale of a few kilometers convection. So you have this individual cloud that can get big enough to give you rain, but not necessarily. Of course, you can get a barrier to your wind, and that's I did my PhD, as I said, in Seattle, and so if you look at the difference between the coastal area in Washington State and the other side of the mountains in eastern Washington, you would see the difference between having a whole lot of uplift, cloud creation and rainfall on one side and the desert on the other side. Or you can have something that looks a bit like this situation, but here the scale is 500 kilometers. So we are talking about circulation that have become much, much larger, and systems that become much more complex, a little bit like the ones that Ali was talking about, where you have you can bring in a whole lot of moisture and you can create a circulation that makes this system much more long-lived and important. And finally, you can have fronts. You can have weather fronts when you have cold air colliding with warm air, and warm air being not as dense as cold air, it slides on top, or it kind of gets pushed up vertically close to the cold front, and you create two regions of cloudiness and rainfall. So we can look at this in these fantastic data sets that we have now, right? So we can look at the entire globe. This is just happens to be 2020, but we've been taking this kind of measurement for quite a while. And so you can start looking at these different kinds of convection and uplift mechanism. And so here is, we are still in January, so it's the winter time in the northern hemisphere, and you see this system developing. These are the classic storms with the comma shaped. They're large, and they can be as big as the entire continent, and they keep coming from the west, moving to the east. At the same time, in the tropics, you see things happening in a very different fashion, right? You see these clouds being organized differently. They pop up like popcorn to some degree. You can see over land, there's a diurnal cycle. They pop up every day. And their structure is much smaller than what we see here in the mid-latitude. You also see, though, that they are also organized somehow. So if I move these along faster, you start seeing bands of precipitation, right? Here we go. This is very clear. There's a whole band of clouds and precipitation happening. And it's in March and April, and we're close to the equator, right? Let's move on a little bit farther. Now we're in May, June, and here we are. So now we see this band has made it all of the other side of the equator. Here is this band of precipitation coming from Africa, moving into the Atlantic Ocean, out to the Eastern Pacific, and along this line. And now let's look over the US. What are we seeing now? Well, we don't really see the same systems that we were seeing in winter. Now we see convection happening in a way, rainfall and clouds happening in a way that is much more similar to what we see in the tropics. These are systems that are very similar to tropical systems. You can just a clear look at the sky tells you that there are these two different mechanisms, right? In the mid-latitude, especially in winter, we have this continental scale ascent in frontal system with warm, moist air rising above the cold, dry air. But even in the mid-latitude system, a lot of the moisture that fuels the most extreme events comes from the tropics, right? It's especially for atmospheric rivers, like the ones that creates those landslide that I mentioned at the very beginning. That moisture comes from the tropics. In the tropics, we have the most severe rainfall comes from these organized system called mesoscale convective systems, right? And the way that they get organized is, again, by creating these conditions where dry air is kept out of the place where we have ascent, and we have a circulation that develops around the storm, and feedbacks between the clouds of the storm and the heating of the atmosphere that make it so that this system can grow larger and more long-lived. And they can move around as a unit. Okay. So when we look at the average, though, right? So we go away from the individual system and we look at the average rainfall. This is the climatology, meaning we've averaged all the Januaries together, all the Februaries together, and we are looking at rainfall and across the globe. And the darker greens are more rainfall. And first of all, I want to stop here and just realize, how magic it is that we know how hard it's raining in the middle of the ocean. This is not something that we've always known, right? This is something that has come with incredible advances in our observational system, so that we can get this bird's eye view of rainfall, which we didn't used to have. And so, when we're going to get to monsoon in a minute here, but I want you to see the entire tropical rain band, how it works, and how it's a unit, it's the coherent unit. And so you see here, as we progress from northern hemisphere winter to spring to northern hemisphere summer, that this rain band expands into the regions that we call the monsoon regions. So how do we define in these days the monsoon regions? Well, we used to think of the monsoon in terms of like what the wind is doing. When people were sailing, that was the most important thing. But now that we really focus more on rainfall. And so we think of monsoon regions as any regions where a large fraction of the annual rainfall just falls concentrated in the summer months. And so we have the Indian monsoon, we have the African monsoon, the West African monsoon that actually extends all the way across Africa. We also have a North American monsoon, right? And then the counterparts in the Southern Hemisphere. But the important thing is that these monsoons are not these just land sea breezes. They are part of this very broad tropical rain band. So they're parts and parcels of that, and their dynamics is very similar to that of the full tropical rain band. So that has helped us a lot understanding how monsoons change. And so so this is a time series of Sahel rainfall. The Sahel is this region, as I mentioned before, that extends from Senegal all the way to Sudan, Ethiopia, Eritrea, and it's just to the south of the Sahara Desert. So this is a region, and you can see here the vegetation, right? So between the rainforest of tropical Africa and the desert, this is a region of transition where rainfall happens in a short rainy season, and it's very variable. And when we normalize the Sahel rainfall index, this total seasonal precipitation, we see we have data from the 1900s, and we see a period that was very wet around the 1950s. And then what really felt locally as a precipitous decline of rainfall. In particular, the drought of the early 70s, and then 1984. People of a certain age here might remember some, concerts that were organized with pop stars trying to raise money to help the victims of the famines that were plaguing Africa at that time. Since the mid-80s, that drought has relented to some degree, but people on the ground have been complaining that it's not quite what, the good times, because the recovery rainfall has been one that plagued by a lot of floods, a lot of events like this one in Ouagadougou in Burkina Faso, where rain just comes down in a deluge. So how do we understand, what causes these kind of changes? For one thing, the fact that we now understand the monsoon to be part of this very global system has led us to understand how it's connected not to local conditions, but to the global condition. And in particular, for the African monsoon, here's a figure of anomalies. The brown here indicates that over this period that is average, we have very dry anomalies across all of Africa. Again, this is the 80s compared to the 50s. And the sea surface temperature anomaly that was coming with it is this pattern of colder in the northern hemisphere and warmer in the southern hemisphere. So we know that the rain band really feels this difference between the northern hemisphere and the southern hemisphere, just a little bit like we showed in the seasonal cycle. And so, and we can use our climate model to figure out where did this sea surface temperature come from. Here is and is it really they that caused this drought? And so here is in black the same anomalies that you saw in Sahel rainfall. Now not normalized, so it's millimeters per day. And then the simulations that use this sea surface temperature anomaly year by year by year, whatever it was historically, to see if we can get these changes. And so you see that the green and the black go together, indicating that we can tell that these global change caused this drought. And moreover, we can tell that this cooling in the northern hemisphere, that's a separate story, but that cooling in the northern hemisphere was really linked to pollution emitted by US and Europe. And so on top of the warming gases that we've been emitting, we've also used to emit a lot of particulate matters and smog, and that was causing some cooling. And so we can figure out what this comes from. The other thing that I mentioned is the fact that extreme rainfall has been increasing quite dramatically. We saw from 1980 to 2024 a 70% increase in heavy rainfall, and again, episodes like the one we saw in Ouagadougou. So right now, about a third of all rainfall that falls in the West African monsoon is considered extreme. This is work that is not quite off the press, is in review, done with a graduate student. And what we've looked at is those satellite images that we saw at the beginning and really tracked those systems, those big clusters of clouds. And we looked at the count. And so we saw that at the beginning of the record, the storms, so this is 1980 where we have these satellite pictures and we can count the storms, and we see that both the regular, let's call them regular storms, and the very heavy, very intense storms were increasing in number until about the 2000s, when things kind of tapered off. But what happened at the same time, the amount of precipitation in each storm that was kind of steady for a while has started to increase quite dramatically. So before we had more storms, and after we had the same number of storms but more intense rainfall. And so altogether, they have given to this region a steady increase in extreme rainfall and floods. So so we're learning that different large-scale variables control different storm characteristics, and what we need more research to find out what controls these rainfall extremes in a changing environment. You know, it could be shear, it could be humidity, it could be a lot of things, and we need to figure out more. And why does this research matter? Why does this research matter outside of Africa? Why does it matter for the US taxpayer? Well, for one reason, what starts in the tropics does not stay in the tropics. These storms that come over the Sahel often end up being seeds for tropical cyclones that then become hurricanes and can hit our own coastlines. But also more generally, understanding the monsoons elsewhere help us understand how our monsoon in North America can work. Understanding organized convection in a place like Africa can also help us understand the severe thunderstorms that happen during summertime here in the US. And finally, when we see a signal as strong as what we saw in the Sahel with those drought and those floods, that's a good signal to benchmark our models. We want to know if our models are good enough to tell what happened in the past, so that we can trust that they're gonna give us good projection for the future. And as we continue to warm our planet, we need to have more information about things that are hard to simulate, like rainfall. And this is, again, something that can tell us if our models are doing a good enough job. And so I want to spend the last minute here just telling you how the cuts affect this work. I work for Columbia, but I'm a research professor, and the Lamont Dougherty Earth Observatory is a soft money grant-funded institution. And grants have been canceled, not mine yet, but other grants have been canceled. And pending grants are kind of stuck in limbo. The program managers don't know how much money they're going to have. Their offices have been decimated. So we don't know. Nothing is coming in. So how long before this research stops? We don't know. And personally, I want to know, where will young go-getters like I was when I was in my 20s that have a real, true passion for science, where will they go if not here? And so I hope that you can help, do contact your representative. Let's stop this funding drought. And thank you for your support.
Thank you so much, Dr. Biasutti, for not only the excellent science talk, but also ending with those slides on why this matters and why our work matters right now. You had a lot of great questions, so I'm just going to start with one from Arturo. So for some context for viewers who are just tuning in, right before this, we had Dr. Allison Wing give a talk about how there are these cloud-radiative feedbacks that are important for hurricane intensification, where there are clouds in the sky, it's really warm, and then where it's warm, we get more convection, more clouds. And so Arturo asked, does this play a role in the organization of MCS?
Absolutely, yes, it does. Hurricanes need to, form only over moist, ocean water, right? They can survive for a little while when they get over land, when they make landfall, but they always form over water. So we don't. But the mechanism of this storm are very similar to the beginning of a hurricane. So you create these situations where moisture is brought in more continuously because you have warming in the same place where you have uplift, and that creates more convergence at the bottom and more uplift. And so it's a positive cycle. It's a reinforcing cycle where the as the water vapor condenses, it heats the column. As the water is present, the long wave cooling is reduced. You warm the column even more. You draw in more moisture air, and you continue the cycle. And so these systems in Africa, they form the same, the squall lines of organization that Ali was discussing. And in this case, the shear of the wind is particularly important in the same way that it's important for severe storms in the U.S. plains. Here we have the strong change in wind speed as you go up in the atmosphere, right at that edge between the hot Sahara and the cooler tropical forest. You have a lot of wind shear, and that helps organize these big storms that then become seeds for hurricanes in the Atlantic. I'm so happy to see people putting things together and learning about this science that I love so much.
Our viewers, like you guys are thinking like scientists making these connections between our talks. It's super exciting and like super great to see that you're staying for more than one talk. Okay, so one last question from Oakstream. So I think this was in one of your graphs about the frequency of droughts. Like there was this increase in the 1940s that seemed as dramatic as the decrease in the 70s and 80s, and they're just wondering, like, is this something that we understand, or are there like some different theories about that period?
So this is active area of research, but here's what we, here's the culprit, that we think are part of this story. One is, we have a warming in the that is due to greenhouse gases, and that warming has been going on longer than just the last 30, 40 years. And so even in the beginning of the century, that could have been part of the story. When the globe warms, it doesn't warm uniformly. The northern hemisphere, where there's more land, tends to warm more. So that would have the same mechanism of creating more a shift of the rain band to the north, and then more monsoon rainfall. And then as the cooling from the sulfate aerosols happens, that would bring it down. The other possibility, though, is that the ocean circulation was doing something similar. So we've if you've been following us for a while, you've seen people talking about ocean currents and the overturning circulation. And the Gulf Stream in the Atlantic is part of that ocean circulation. And so that can move heat around. And of course, we don't have great measurement of ocean circulation decades back, because that's a very hard thing to measure. So we're still working out the details of that, but it could be a combination of both things: some natural variability due to ocean changes, and some forced signal due to the warming happening already from greenhouse gases.
Okay, so that's all the questions we have time for, but we, had a few viewers in chat say that they are those like early career scientists that you were referencing, and they're super inspired by your talk. So thank you again, Dr. Biasutti. Everyone say thank you in chat. And now we are hour 21, I think. So I'm going to hand off.
So hi, everybody, and welcome to, I think he said hour 25 of the live stream, somewhere in there. So we have about 75 more hours to go, and I have not watched every minute, but I've watched a lot. It's been really great. So again, I want to thank the organizers for putting this together. So are we ready to go with our next speaker? Looks like we are. So let me introduce our speaker. Jacob Cohen Jacob is a PhD student in physical oceanography at the University of Washington, where he studies air-sea interactions and climate variability with Dr. Louann Thompson. He earned his BA in physics from Carleton College in 2019 and focuses his research on the Southern Ocean using satellite observations to understand how oceanic and atmospheric processes influence air-sea heat exchange on seasonal timescales. So hopefully, Jacob, I got all that right. If not, correct me, but otherwise, welcome and take it away.
Yeah, thank you. Yeah, I'm Jacob. I'm a PhD candidate at the University of Washington in my final year. Today, I'm going to talk about some work I've done with marine heatwave forecasts. But yeah, I've done a lot of research, Southern Ocean air-sea interaction as well. So thank you for having me. Today, the title of my talk will be Marine Heatwave Forecasts Toward Operational Forecasts of Ocean Extremes. This work has been funded by a variety of sources, but federal funding has come from the National Science Foundation and has really supported this work. And I'll also highlight some work from the National Oceanic and Atmospheric Administration, or NOAA, and tools that I've used from the National Center for Atmospheric Research, which is an NSF-funded lab. So I'll start with just the basic definition of what is a marine heat wave. Simply put, it is an area of hot water or a hot water event in the ocean. These changes are transient and extremely warm relative to what we expect. So if we just looked at the hottest temperatures, we'd see heat waves in the summer because it's hotter in the summer. But here we're talking about extreme heat relative to the expected conditions. So relative to that seasonal cycle and the location in the world. So here I'm showing just a snapshot from 2016, where there were a number of heat waves around the world. And if you look specifically at the US, you can see a lot on both the northwest coast of the US and the east coast of the US. Marine heat waves are really important to study and understand because they drive ecosystem disruptions, and these have local impacts. So here I'm just highlighting three: toxic algae, fish and seabird die-offs, and the negative consequences that these have for industries, especially fisheries on our coasts. All of these impacts are directly associated with a single marine heatwave event here in Washington in 2016. So if these are just from one event, you can imagine that around the world and around the US, lots of different events can really disrupt both ecosystems and industries that people rely on. If, like me, you follow climate news, you might have seen that recently. This article is just from last week in The Guardian. An unprecedented marine heat wave has been occurring near Ireland. This has garnered a number of articles in the news and popular media because of the effects that it will likely have on the ecosystems near Ireland, and as a result, a lot of the industries there. So these events are really important, and today I'm going to talk about how we forecast them, what the current state of prediction is that we use, and some of my work that may help create new types of predictions and new ways of communicating predictions. And all of this is reliant on the funding that we get from the US government. So I'll start by highlighting some of the work currently that is going on. The closest thing we have to operational marine heatwave forecasts come from the National Oceanic and Atmospheric Administration, which create these monthly forecasts of marine heatwave probability. If you go to the link here, if everyone goes to the link here right now, then it will probably crash. But if you save the link and go check it out later, there's a really cool dashboard. You can flip through different years and months and different forecast timescales to see how our models predicted marine heat waves and what may have occurred. You can also toggle between including the long-term temperature trend in what you consider an extreme event. So right now, this is showing without removing the long-term trend, we see that a lot of the ocean is likely going to experience a marine heat wave this month for forecasts that were started at the beginning of the month. If you remove that long-term trend, you see that fewer places are expected to experience extreme conditions, but I'll highlight a couple. First, there's this spot in near the southern coast of Africa that is at 100% marine heat wave probability. And then you can also see, if you look at Ireland in the Northeast Atlantic, you can see that marine heat wave that article was about. That marine heat wave was predictable, and we did see that coming. The group at NOAA that makes these forecasts and compiles them, they also publish a monthly report on the expected or predicted marine heat waves in different parts of the ocean. This is a super interesting read if you sign up for these emails, and hopefully these become eventually operational. Right now, these are all just experimental forecasts to be used for research purposes or by people who are interested. But so far, they have not been turned into official forecasts that are used by like widespread industries. So very recently, this will actually be published next month, but this paper is published online already. A group published a paper called "What Makes a Marine Heatwave Forecast Usable, Useful, and Used." So useful, by that they mean, is it giving information that could be helpful? Is the forecast skillful? Is it using lots of different observations and data to come up with that forecast? Have we checked it? Usable means we have checked it and it is skillful. It is outputting relevant product for different industries and different end users, and it comes with visualizations and delivery that makes it usable by the end users and the industries that might find it useful. And then finally, used means it's actually being used by people. It is being created with the end user in mind. We are engaging the end users in the creation of these forecasts. We're updating them and communicating them at relevant timescales to the people who may use them. So far, I don't think we're at this point. We don't have useful, usable, and used marine heatwave forecasts, though there are examples of times where individual forecasts or predictions have been used and have been able to mitigate some of those impacts on ecosystems and industries that I mentioned before. So kind of my big vision for the future is, what if we could have these marine heatwave forecast cones? So here I'm showing just a hypothetical forecast of a hurricane that is coming towards the US. And we've all seen these types of visualizations where we know where it is currently, and then we can see where it might go in the next couple days. This is up to a 5-day forecast. So what if we could do these for marine heat waves, where we have where the event is right now, and then we can predict where it's going to go, where it might impact in the next several months. So a big difference between hurricanes and marine heat waves is that there's not necessarily a clear physical driver that is moving marine heat waves. Also, the time scale that these events are occurring on is much longer than 5 days. So we are actually thinking about forecasting these months up to a year ahead of time. So this does provide much different challenges than forecasting hurricanes, but these types of visualizations could provide really interesting and intuitive ways to communicate information to both end users and to the public. So this is where my work comes in, looking at object-based forecasts of marine heat waves. So how do we go from our climate model forecast of sea surface temperature on the left to predicting these spatial events that can move through time on the right? And I'll take a step back and think about first how we can come up with these in the first place and how we can evaluate how good they are. we can't just throw out this cone of uncertainty for a marine heat wave without understanding first if that is a useful prediction in the first place, if it has any physical meaning, and if it is skillful. So to study that, what we do is we look at a climate model forecast of the past. So we use what is called the CESM2 Seasonal to Multi-Year Large Ensemble, which is a collection of forecasts that we initiate in the past, and then we can compare them to what actually happened. So every February, May, August, and November over the last 50 or so years, other people at the National Center for Atmospheric Research have initiated this forecast for 2 years, 20 different times, so we can get 20 different possibilities of what could have happened from, for example, August 2009, run that forecast for 2 years, and then we can compare it to what actually happened to evaluate how well our forecast performs. So I'll walk you through how we get from those sea surface temperature forecasts that come out of these climate forecasts to forecasts of these spatial extreme events. So here's just a snapshot from a forecast initialized on February 1st, 2010, forecasting 3.5 months into the future, the May 2010 average sea surface temperature. And this is just one ensemble member forecast. So from that sea surface temperature, we can subtract the average conditions over the whole climate model forecast to get what we call sea surface temperature anomalies. We can then sub-select the most extreme of those anomalies. So here we decide that if the temperature is within the top 10% of May temperatures, then we consider it to be a marine heat wave. We then use a program called OSTRAC to essentially smooth and draw lines around these areas. So now we've gone from just individual grid cells that are experiencing marine heat waves to these distinct spatial marine heat wave events. And finally, we can compare those to the observations. So now the predicted events are in the solid colors in the bottom left panel, and the outlines are where we actually observed marine heat waves during May 2010. And we can see that some of the time we are predicting these marine heat waves, though we're also predicting some false alarms in some places and missing observed events in others. So we can take all of that information and do this for every prediction over a whole 30-year period to understand how good our predictions are at different times. So one metric we can quantify is the false alarm ratio, which tells us what fraction of forecast marine heat waves were not matched or did not occur near observed marine heat waves. And we see that at 1.5 months of lead time, so forecasting a full month ahead, we see that we have pretty low false alarm ratios, which means we're doing a pretty good job at matching these events, that we're predicting them nearby the observed marine heat waves. And as we go further and further, forecasting out to 3 months, 5 months, and 7 months, then we see that we're getting more of these false alarms, but overall, we're still doing a pretty good job. We can also look at how close our predicted marine heat waves are to the observed marine heat waves. So on the top, we're looking at the distance between two events, the predicted event and the observed event. And we see that at 0 months of prediction, we have the best results. And then our predicted marine heat waves get further and further from the observed marine heat waves. But if you see the dashed lines here, those are for random forecasts, and our climate models are doing better than random forecasts, at least up to a year ahead of time. And on the bottom, we're predicting how much overlap there is, or we're showing how much overlap there is between the predicted marine heat wave and the observed marine heat wave. And again, really up to 15 to 18 months, we're doing better than the random forecast with this climate model. We also look at the predicted marine heat wave area and intensity and compare those to the observed events. And the same thing occurs up to at least 1 year. Our predictions are doing better than a random forecast would at predicting the size and the intensity of these marine heat wave events. So overall, we see that our predictions are doing pretty well. And to bring it back to this kind of view for the future of creating these marine heat wave forecast cones of uncertainty, we see that these object-based forecasts using these spatial events as opposed to just predicting marine heat waves at every individual location of the ocean, we do have skillful predictions of those, and they could potentially be used for climate communication and potentially end users eventually. So this work should be published next week, I think. It's been accepted and hopefully will eventually be used for seasonal forecasts of marine heat waves. I'll end with a little example of how these forecasts can be used to really highlight their importance. This is a question that I had when I started working on this and that I get asked a lot is, okay, so we have these monthly forecasts for marine heat waves, but how is that actually going to help if we know that one's coming? So I'll just point to one example from the Northwest Atlantic Ocean off the coast of Maine. This was an article written in 2018 about differences between a 2012 marine heat wave in the Northwest Atlantic and a 2016 marine heat wave in the Northwest Atlantic. So in 2012, on the left top panel, we had a marine heat wave in Maine, and in 2016, there was a very similar marine heat wave in Maine. But people learned from what happened in the 2012 event, and they actually shared a forecast for the 2016 summer of elevated temperatures with different marine industries and lobster market members and fishermen. And we saw that the lobster landings, the seasonal cycle of the lobster landings in 2012 and 2016 looked very similar. But for the annual cycle of lobster prices, in 2012, there was a huge dip when there were all of these extra lobsters early in the season. The market responded kind of drastically and suddenly, and this was bad for the fishermen who were relying on lobster prices. But in 2016, because that increase in supply and demand was expected, the market was able to respond at a much more gradual rate, and this led to a much better season for the lobster fishermen. So that's just one example of a forecast actually being used, but there are others around the world that highlight why this work can be important and why future funding for marine heat wave prediction is necessary. So I'll leave some of these takeaways up on the screen, and I'd be happy to take any questions. Thank you.
Thanks a lot, Jacob, for that talk, everyone. Let's thank him in the chat. Thank you. So we have a bunch of questions, but let me take host privilege here and ask the first question. This is something I've always wondered. So as an atmospheric scientist, I understand what causes heat waves in the atmosphere. You basically have a high pressure system. You have air, you have air descending in high pressure systems, bringing down air from aloft. You end up with a very dry column, no clouds. You have sunlight hitting the ground. What's the physical mechanism that's driving these marine heat waves?
Yeah, that is a great question. I kind of highlighted the exciting aspects of this work that might be exciting for a general audience, but a lot of our work in our group and work that I'm involved in is looking at the physical drivers of these events so that we can understand them better. Broadly, hopefully not too broadly, marine heat waves are often driven by the atmosphere, extra radiation from the sun, lower wind speeds. We get a shallower mixed layer in the ocean, and then it heats up faster. There are some events that are driven by advection in the ocean, but primarily they're driven by changes in the atmosphere.
Okay. Interesting. All right. So let me ask the questions that were in the chat. Or a few questions that the directors have picked out. I wonder from Ink Chimera, I wonder how oceanic heat waves affect inland weather.
Yeah, there is some research on this, I think, that marine heat waves, I think I've seen examples in the Pacific Ocean where marine heat waves can then be precursors to continental heat waves over the US, and can be precursors. They're often caused by similar patterns in the atmosphere. So it's not necessarily that the ocean is driving the heat wave on the land, but they're being driven by the same thing, and the ocean can be an earlier indicator of continental heat waves of the US.
Kathy Ann Caesar writes, where can I find more information on your heat wave forecasting? We are in the Caribbean and work on various variables, SST, STH, and passage of TC tropical cyclones. And it's an Aggie. Whoop!
Yeah, I would definitely check out the website from the Physical Sciences Lab at NOAA. They do a lot of really cool work. It's, again, the closest thing we have to operational marine heatwave forecasts. It is at a pretty large scale. I don't know if there's anything like this at smaller scales, which is really what you would need for any sort of operational forecast or to look at very specific locations. But this is definitely a good place to start.
Astra H writes, what about anomalies of excess cold? Do they have less of an effect?
I'm focused on marine heat waves, but marine cold spells are definitely a thing that people are thinking about. Similarly, you would expect that they would have detrimental impacts on ecosystems and fisheries. But part of the effects of global warming is that, right, if we're not including the global warming, then we have these heat waves that might be driven by other things. But if we look at this recent plot, much of the world is going to be experiencing extreme heat events more often than extreme cold spells.
So were you living in Washington in the 2021 heat wave?
Yes, yeah, I was.
So I mean, that really, I mean, the water temperature off the coast was really high, and that had can you talk a little bit about the effects on the ecosystems? I mean, I remember hearing maybe it was Jane Lubchenco or somebody like that talking about, billions of starfish and other animals that were killed by that.
Yeah, lots of examples of different organisms and fish and seabirds that were really negatively affected in 2021. There was also, kind of starting in 2019, there was a big heat event in the Northeast Pacific off the coast of Washington that once it reached the coast, a lot of its effects were felt. But even when it was in the more open ocean areas, had caused a lot of changes on the biogeochemistry of the region. Yeah, I don't know too many other specific examples of the effects, but it was definitely felt. And that marine heat wave was in the news a lot more than a very similar event only 4 to 5 years earlier. Once we started seeing indicators that another event in the Northeast Pacific was going to return, people got really worried because they knew the effects that it could have on industries and ecosystems.
Sort of as a follow-up, how do the heat waves actually influence like animals? Is it just they're warming up, so they're changing the metabolism, like, put humans in a hot room, or does it change like the amount of oxygen in the water? Does it have sort of knock-on effects that aren't directly doing that?
Yeah, it's both. I can't speak too much to the specifics of how different organisms are responding. It does affect oxygen in the water, and the properties of other chemicals as well. And for this example, in the Northwest Atlantic, it led to much earlier landings for lobsters. So they were coming on shore much earlier. Supply was much higher early in the season, and this led to kind of a drop in prices to meet the demand. So it changed the behavior and the location of these organisms because they were moving based on where the heat was.
I should say that was a question that I adapted from something Matt Luongo put into the chat. And Michael N. Evans writes, how do your results compare with what you would get from CFS as done for the Coral Reef Watch product?
Yeah. So this product from NOAA that I included, this is using the North American Multi-Model Ensemble, which I believe includes CFS as one of its models. My results are from the Community Earth System model from NCAR, but they compare very similarly to the results from the North American Multi-Model Ensemble, and I presume from CFS as well.
So on sort of a more personal note, like how long have you wanted to be a scientist? How did you sort of get where you are today?
Yeah, I studied physics in undergrad and was always interested in climate and the environment. I ended up, like many other speakers have said before, I did a REU, or Research Experience for Undergraduates, which is a National Science Foundation program. I did that at Penn State University, got introduced to oceanography, and it kind of checked all the boxes of the things I was interested in. And the next year, I ended up at the University of Washington.
Yeah, no, I think these REUs, so if people have never heard of an REU, Research Experience for Undergraduates, they're usually programs that are run by universities that bring people who may not know what being a scientist is into a university setting where they can actually see, spend a summer being essentially like a grad student light or something, doing some research, because otherwise people don't know what it's like to do research. Do you remember what you did during that Penn State?
Yeah, I looked at data from Argo floats, which are these devices that are located all over the ocean and take measurements of temperature and salinity at a variety of depths in the ocean. And we looked at what they could tell us about local ocean circulation in the North Atlantic. I had never done anything related to oceanography before then, so it was a really cool experience. And I got to learn from a lot of really cool people who knew way more than me and kind of just introduced me to a ton of different topics, both within oceanography and atmospheric science and climate science generally.
Yeah, one of the points I always like to make is that scientists don't appear fully formed out of thin air. You need to create them. And we have the US has this very efficient system to create scientists. We have this pipeline, REUs, we have grad students. It's all funded by the federal government. And if funding gets cut, what you're doing is essentially you're cutting off the flow of scientists. And I don't think anybody would ever say the US has too many scientists. But that's certainly what's going to happen if we cut off funding for that. So we're approaching the end. Do you have anything else that's come up or reminded you, Jacob, you want to say in the last minute or two?
I don't think so. I appreciate the time and you for hosting, and everyone online for watching and supporting this live stream. Thanks.
Thank you. All right, well, that was great. So let me find my little statement I'm going to read as we change over speakers. Thank you for joining us at I forgot exactly what hour it is. I think it's around 25. I'll have to ask the host in a second. Of the Weather and Climate live stream. We have about 75-ish hours to go, and we're thrilled that everyone is here with us. My name is Andrew Dessler. I'm a professor at Texas A&M in the Atmospheric Sciences Department, and I'm going to be your host for this segment. We've seen a lot of really excellent talks so far. We have a great speaker coming up, which I will introduce in 1 second. But before then, just a brief reminder that all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of their host institution, funding agencies, or other participants. But we're here with a purpose, and the purpose is that you all deserve good weather and climate forecasts, the kind that save lives during hurricanes, help farmers plan their crops, guide families making weekend plans. And, the U.S. has built this weather and climate infrastructure that really is, world leading, doing fundamental cutting edge research. And it's something that we all own. So, you should think about this as something that you own that's of tremendous value. U.S. scientists have been leading the efforts in weather and science, funding cuts are really threatening all areas of weather and climate. So we're seeing weather stations short-staffed just when extreme weather is becoming more frequent and dangerous. Climate research labs that have operated for decades are shrinking or shutting down, taking with them irreplaceable experts and decades of climate research and expertise. So we need your help to save our forecasts. There's information about contacting your representatives available through the link, which is rolling across the bottom of the screen right now. So please do that. Let me assure you, I've talked to a lot of people on Capitol Hill. If you call your representative, they care about that. Emails are okay, but calling them means you took the time to pick up the phone and call. A lot of people won't do that. And so they know that every person who calls, there's 100 people out there who agree with them who really can't be bothered with calling. So a call means you have a lot of leverage. Now, it still doesn't mean they'll listen to you, but at least you've done your duty and you have brought it to your attention. This is something you care about. So definitely call. I mean, people will be polite. They're not going to yell at you. Their job is to listen to what you have to say when you talk to the person at the switchboard. So definitely you should call and get in the habit of calling. I think as people who've lived in a country that's really well run most of the time, we've kind of gotten out of the habit of this sort of participatory democracy. People don't vote, people don't call their representatives. Learn how to do that. That's a skill that we need to be doing. Okay, let me check to see if there are any messages for me in my, let's see. Okay, I think we're good to go. All right, so our next speaker is Professor Paul Bierman. Paul is a professor of environmental and natural resources at the University of Vermont, where he's been since the early 1990s. He's a geologist whose research focuses on the interaction between people and the Earth's dynamic surface. He graduated from Williams College in 1985 with a major in geography and earned his PhD also in geography. He's the author of the recent book, When the Ice is Gone, about Greenland's ice sheet history, and his research has taken him around the globe studying climate erosion and ice sheet dynamics. So Paul, hopefully I got all of that right. If not, you can correct any mistakes I made. But welcome, and I'm really looking forward to hearing your talk.
Great. Thanks, Andrew. Hear me okay?
Yeah, great.
Great. The only correction I'll make is I'm a geoscientist, who does a lot of geography in that sense. Thanks for having me. And this talk is going to be a contrast to the last one, although there's a similarity in that Jacob and I both went to the University of Washington, and I have really fond memories of that place. But I'm going to take everybody north to Greenland and to the medium time history of Greenland. It's not weather for sure, it's paleoclimate. And I just want to acknowledge at this point that a lot of the research I'll be talking about was supported by the U.S. National Science Foundation, numerous grants over 30 years that got us to where we are. And I'm going to be talking a bit about some of the material that's in the book I published last summer, When the Ice is Gone, about Greenland, its history and climate. All right. So the overarching purpose of my talk today is to show that geologic and human history clearly show that climate and weather and the science needed to understand both are important to everybody across the political spectrum. And I think this cartoon does a great job of showing that as the climate changes, whether it cools or warm, it affects everybody. It affects people no matter how you voted. And it really should be a nonpartisan issue, that we support science that saves lives and makes people more prosperous. One of the things I've been thinking about a lot as I did the research on this book, and particularly in the last 3 or 4 months, is that the US military actually started climate change research in the United States and accelerated it dramatically during the Cold War. This is one of several essays I've written in the last few months, and I think those will be tossed up in the chat at some point. And this one is about how the US military has cared about climate change since the dawn of the Cold War because it influenced their operations. And again, I think this is really important to consider the basic science upon which what all of us do today was built. I'm going to talk a bit about Camp Century, which for those of you who don't know it, is this really unique under snow base. The Army built this inside the Greenland ice sheet. It housed 200 men. They started in 1959. That's before I was born. It's a long time ago. It absolutely was not top secret. It was featured in the February issue of Popular Science in 1960. That's the cover of the magazine with the title, "The U.S. Army Builds a City Under the Ice." The building was done using these massive plows imported from Europe. They would dig trenches. The longest trench was 1,000 feet long. And then the Army would place buildings in those trenches. It had electric power generated in large part by a nuclear reactor inside the ice sheet. And the fact that it had that nuclear reactor allowed all sorts of things you wouldn't expect to go on inside the ice to happen, such as unlimited hot showers for the men and running water. They had essentially infinite water source because they could melt the ice sheet. They had power. They lived at 72 degrees, even though it might have been minus 50 on the surface of the ice sheet. So a really spectacular place. And not only was it a military base, but it was a science research outpost in the Arctic, collecting weather data, collecting climate data over various timescales, and understanding how people could work in really extreme environments, which has been translated today into our ability to collect ice cores and to do research in remote locations like that. This is again out of the Popular Science, and it just shows you the layout. The men lived in heated prefabricated barracks, again, all inside an ice sheet. They got their water by melting that ice sheet. A steam drill drilled a well, and then they used the same steam jets to melt the ice. Nice piece of trivia, the men living inside the ice sheet were drinking water that was melted from snowflakes that fell about the time of the American Revolution. So think about that. You're up there for 3 or 4 months and you're drinking water from the time that George Washington was fighting for the independence of our country. They also did climate science. And the Army cared about climate science because the 1940s had been unusually warm into the early 1950s. And they were really worried about operational activities in the Arctic and in cold places. And so a fellow named Henri Bader, that I go into a lot in the book and I won't go into today, but he pioneered this idea that the history of Earth's climate was preserved in polar ice at both poles. And that the way to get at that history was to drill and to collect ice cores. And this is the drilling setup at Camp Century. They had the wonderful support of having electricity, of having a place outside the wind in these trenches to drill, of having 3 or 4 hot meals a day and places to sleep, which made it a whole lot easier for them to drill. Still took them 6 years to get through the ice sheet because they were really pioneering ice coring at that point. They were the first to drill through an ice sheet and recover a core ever. They recovered 1,348 meters of ice. That ice was used by Dansgaard and his collaborators to describe the climate of the last 100,000 years, a momentous paper in 1969 in Science. But then they kept drilling and they brought up 3.4 meters of frozen soil. That too was a first. But back in the 60s, people really didn't know what to do with that frozen soil. And due to several men, Chet Langway and J.P. Stephenson in Denmark, that soil has remained frozen since it came out of the hole in July of 1966. It did take a trip to Denmark, and I won't even use the word lost, just that much of the community was unaware of where these samples were. That's a color photograph of the bottom of the core. For those of you who are glacial geologists, that's frozen glacial till from the bottom of the ice sheet that they're looking at. And in 2019, we were invited by the Danes to a small workshop in Denmark, and and shown that this core was perfectly frozen in Danish ice core freezers. That's me with the red hat, not wearing enough for minus 27. And the Danes provided us several samples from the top of this material and the bottom. And at the University of Vermont, we took these samples apart. We collaborated with about a dozen people from around the world to understand how old these samples were, the history of climate that was preserved in these samples, and what they could tell us about the stability or the instability of the Greenland ice sheet. When we processed these samples, we were really concerned about saving every gram. We only had a couple 100 grams of material. One of the jokes that my postdoc at the time, Drew Christ, used to make was that there were many, many times more moon rocks than there was this material from underneath the ice sheet. So we better be damn careful with it. So when we washed the samples through sieves, we saved all the water, and then we filtered that water. And if you watch this video, you're going to see some small flecks of material that are flowing out of that bin and onto the filter apparatus we have here. And I looked at those flecks and I kind of recalled 25 years formerly in my career when I worked on lake sediments and lake cores for understanding climate back through the Holocene, the last 10,000 years. And remembered a trick we used to do when we wanted to find fossils to date, and that was to mix the muck from the lake in water like this and then go have lunch and come back. And the little fossils, the bits of plant material would float. And I remember saying to Drew, I think there are fossils in this stuff. And Drew made comments I won't repeat online about how crazy I was and expletives and all that. But indeed, when we popped these under a microscope, that's what we saw. So I think any of you in the room, however you are trained, science, not science, atmospheric science, climate, geology, will look at that and say, that looks like a twig. And that's exactly what we did. That's the first photograph we ever took, staring down the microscope with a cell phone camera. We were seeing twigs, and we were seeing mosses, and we were seeing seeds, and we were seeing bits of insects. We didn't at the time know how old that material was. We do know now that that material is about 400,000 years old. That's one of the times in the past when Earth warmed up dramatically, and we know that ice sheets shrank. So now at Camp Century, far northwestern Greenland, we know that the ice vanished 400,000 years ago. Nearly a mile of ice melted away during a period of time that was about as warm as it is now post-industrial. And that is a huge warning to all of us that if we keep the climate this warm, we are going to lose a significant portion of the Greenland ice sheet. So started working with a series of paleobotanists, Ola Benecke from Copenhagen, Dorothy Petit from Columbia, and then Hallie Mastro, a master's student working with us, who identified thousands of fossils in the eventually 28 samples we had from this core. And the wonder of paleobotanists is they can look at a scanning electron microscope photograph like this one here in gray, and in their eye, they don't see a broken up piece of wood, but they see the plants on the landscape, and these were tundra plants. Or they can see a seed, that's a poppy seed, unlike the poppy seed on the bagel that you might have had for breakfast or for a snack last night. And from that poppy seed, they see an Arctic poppy like this, that again defines a tundra ecosystem there. Or they might have seen a fossilized midge. These are the things that fly around in the Arctic and congregate behind your ears and annoy you. Perfectly preserved in this frozen soil from beneath the ice. So from a core that was drilled in 1966, now we had a view, and I say we, a team of more than 40 people, 5 countries, 7 graduate students, working under National Science Foundation funding. We had a view of what the landscape looked like in Greenland 400,000 years ago when the ice was gone. So various people have run models. This is from Jörg Schaefer's 2016 paper of what the ice sheet might look like as the ice vanishes. And none of these are unique solutions, but they give you a very clear idea that, today about 80% of the island is occupied by ice. And the 3 dots are the Camp Century core up here, the GISP-2 core here, and the Di-3 core here, all deep cores that have penetrated the ice sheet. If you lose about 50% of the ice, then Camp Century is absolutely clear, but GISP-2 is still under ice, and so is probably Di-3. 90% ice loss, it's a very good chance that either GISP-2 is shallowly covered or isn't covered. Di-3 is out here. 95% ice loss. All of these are open. And so we knew Camp Century, but we really didn't have a good clue of what was going on for the other two in terms of age. Jörg Schaefer has published a paper that suggests within the last million years, the GISP-2 site was free of ice. It could be much younger than that, but it's at least within the last million. And then Hallie took a look at the sediment that came up from GISP-2, and what she saw were more fossils. So poppy seed again. There's some spores and parts of soil fungi in here. But now we know that the ice was gone at GISP-2, replaced by a tundra ecosystem within the last million years or less. And it was gone from Camp Century 400,000 years ago, another tundra ecosystem. If we lose the ice at Camp Century, the modeling that Ben Kiesling and others have done suggests at least 1.4 meters of sea level rise. That's about 5 feet. But it's possible that losing ice at Camp Century gives us as much as 7 meters or 24 feet of sea level rise. And we know now, as I said, from these fossils found at GISP-2, that the center of Greenland's also been ice-free. All right, so I'm going to borrow a quote from Wally Broker, who passed now 6 years ago. But Wally has a quote that says, "Climate's an angry beast, and we are busily poking at it with sticks." Now that we know that Greenland was ice-free at temperatures similar to today at 400,000 years ago, I think we know that unless we change our ways, this is going to happen again. All of the climate forecasts we have suggest if we continue putting CO2 into the atmosphere, which we're doing today, and we don't get it out, we are going to warm the planet significantly. So I'm going to replace climate here with Greenland and say that Greenland is an angry beast that we are busy poking at with sticks, those sticks being a warming climate. And of course, we all know this curve, the Keeling curve, that carbon dioxide is continuing to rise rapidly in the atmosphere. I was born somewhere at about 315 ppm. The latest observations that I saw a couple of weeks ago were 430 ppm. It's a 50% rise over when I was born. And we know, just looking at the temperature record, that every month of the year, if we take the global average over the last 40 years, has been getting warmer and warmer and warmer. And last year we saw 1.5 degrees C. And the result, of course, is melting ice. That melting ice is going to affect everybody everywhere around the world's coasts. And this is an animation that The Guardian published last year that I like particularly because I spent a lot of summers visiting Provincetown, and this is a view that I know well down the center street in Provincetown. But I think these kinds of animations really bring home that Greenland has really long arms and they reach around the world. And so the melting of the ice sheet in Greenland, the melting of the ice in Antarctica, the melting of alpine glaciers, the thermal expansion of the ocean as we warm the climate, is going to have real effects on people, their lives, their businesses, and their vacations in a place like this. And when I teach climate, it's these animations that are the most universal in getting students to realize that this is something they need to care about. So if you want to learn more about what I've talked about, there are a couple sources. The book, When the Ice Is Gone, for sure, that published last August with W.W. Norton. It's going to be in paperback this fall. And if any of you listening are interested in teaching with it, I would love to talk to you. Just drop me an email. We're working on some plans for lesson plans for teaching with it, for climate, for history, for ice cores. And it tells the history of Camp Century, not just from the science, but really from the environmental history. This is a cartoon at the time out of an American newspaper in 1959 that gets just about everything wrong. I'll leave it to you to decipher all those things that are wrong here. It also talks about the military history of the Arctic and the weather and climate observations that the U.S. Air Force was making at secret bases within the Arctic. Talks about the men and the women who were integral in collecting this frozen history and keeping it to interpret the Earth's climate. And it talks about the science that the group of us have done over the last 5 years to decipher what was in that core. The other thing you might be interested in is a film produced by Kathy Kasich. This was also supported by the U.S. National Science Foundation. She's professor at Sacramento State University, a professional filmmaker. It's called The Memory of Darkness, Light, and Ice. And I would have played the clip, but I think given our technology, you would have seen it, but not heard it today. So I'm just showing the poster for that. If you would like to screen this film, it runs about 58 minutes. You should first find a good space for it at your institution. Then if you get in touch with Kathy at metamorphfilms.com, she can send you a screening copy that you can show at your institution. It's great to do this with a panel discussion from folks that I've heard, so you might want to pull some people together about that. But it's a good way to start discussion about the importance of climate, the relationships to sea level and ice sheets. I'm going to finish by just highlighting another piece that I published in the last couple of weeks. This is in an outlet called The Conversation. It's free to read. And it's an outline of why cuts to the National Science Foundation endanger research, as I said in my title, that improves economic growth, national security, and your life. And the lead paragraph of this is simply that if you look at the mobile phone or the tablet, here's my Apple phone here, the touchscreen technology, the speech recognition, the digital sound recording, and even the internet were all in part developed by funding from the National Science Foundation. So really, no matter where you happen to live or what you happen to do, the basic research done by scientists supported by NSF have helped all of our lives. And again, that is irrespective of who you might have voted for now, in the future, or in the past. Two graphics here from this piece I just wanted to share with you all. First, that investing in science and engineering is really an investment in all of America. This is a map of where NSF grants went by state in 2024. And they're colored all in blue, but many of these states did not vote blue. And I think that's an incredibly important thing to remember in this country that is politically divided right now, is that National Science Foundation dollars flow to the entire country and to all Americans. And this one, to tie back to the theme, and I'll close with this, is that the National Science Foundation funded some of the earliest weather equipment that went onto satellites. This is a 1958 Navy satellite that was launched, and it monitored cloud cover on the Earth. And the research to put this satellite together was funded by the National Science Foundation. So I'm going to leave you with that, and we got a couple moments for questions. And I hope that in the chat are some of the links of the articles I've mentioned.
Well, thanks a lot, Paul. That was really excellent talk. Everyone thank Paul. Imagine a round of applause. So what happened to Camp Century? I presume people aren't still there.
No, it'd be a tough place to be. Camp Century was abandoned right after they finished the drilling in 1966. Group went back in 67 to pull out some fuel. They left everything else there except the nuclear reactor. We could start with the millions of gallons of sewage from 200 men that lived there for 8 years. PCBs, asbestos, construction materials, it's all in the ice, and it gets buried every year by a portion, a meter of snow. So it's about 30 to 40 meters below the surface right now. It is in the accumulation zone. But predictions suggest that within the next century or two, it will enter the ablation zone, and all of that material eventually will melt out at the surface of the ice sheet. And that would include all the leftover frozen steak and turkeys and things that they left behind. So we will not live to see that, but our children's children just might. So no, you can't get to Camp Century today, and the ice has completely crushed it. When they went back in 1969, they could barely crawl through the tunnels. The deformation of the ice had closed the tunnels.
Yeah, I mean, I think people don't appreciate that. You know, the ice flows. The ice is flowing. So you put a big structure like that, unless you put it in a place that, you know, you really don't expect there to be a lot of movement, it's going to get sheared, and, you know, it's I don't know what the time scale for that is, but apparently short enough.
The time scale was very rapid. On average, the walls of the trenches were closing about a foot a year, and the Army spent a lot of time trimming the walls and getting the snow out. So yeah, it's rapid deformation. And of course, as those who do glaciers know, with Glenn's flow law, the warmer the ice gets, the faster it deforms.
Right. All right. So we have a question in the chat from Elizabeth Leghorn. How do you use the information from the cores? How can you apply it to current day?
Sure. So we use the information in the cores to understand when the ice sheet melted in the past and what the ecosystem that replaced the ice was. This is important because we need some kinds of analogs for what's happening today in terms of warmth on the planet. We can model, and that's great, and they're very informative models of what might happen, but having the ground truth is really important to test those models and to validate the modeling that we're doing. So we look at ourselves as geoscientists providing the ground truth, and I should say more than geoscientists, but biological scientists, botanists, all a group of people, to say, hey, here is the data, here's what's real. That's on the scientific side. I think what is most important with the talks I've given to a wide variety of groups is that it's really, really tangible when you show pictures of fossil plant material from underneath an ice sheet. I've done a lot of elder education and people who might just completely shut down when you use numerics and models and graphs and all that. The minute they see a picture of these fossils light right up and understand that the ice is fragile and it has melted. So I think there's an emotional piece to this of finding fossils under an ice sheet that has had far more impact than maybe anything I've done in a 40-year science career in terms of public outreach and getting the public to understand why it matters to stabilize our climate and to protect the ice on this planet.
Good answer. Good answer. So I have a bit of a technical question about that Provincetown. So, you showed the water going up, and even at 6 feet, I think things there are still overpriced, I'm sure. But the thing, so the thing I always, so I don't know a lot about this, so correct me if I'm wrong, but Greenland exerts its enormous amount of gravitational pull on the ocean. So it's actually pulling the ocean towards it. And so if you melt Greenland, the water actually is going to run away because it's not being pulled. And so Provincetown, I thought, was in that zone where sea level rise wasn't actually going to have that big of an impact. It's on Massachusetts, for people who don't know, or Provincetown. It's right on the tip of the part that's sticking out into the Atlantic. So can you comment on that at all? Is that something you know much about?
Absolutely. So there is completely the near field adjustment to the mass, the isostatic adjustment to the mass of the ice on Greenland. And so the ice itself is, and I know this sounds counterintuitive, it's warping the sea surface because of that gravitational attraction. So as ice melts on Greenland, two things are going to happen proximal to Greenland. The first one is that the weight of that ice on the Earth's crust will be diminished, and the Earth's crust will respond by rising. But the other thing that will happen is the gravitational pull of that ice will diminish and the water level will lower. So in Greenland, they're actually suffering the opposite effect. And we can detect this with the modern GPS network. Greenland is rising. And they, in 100 years, are looking at some of their ports drying out. So there's a whole other issue in Greenland. And I didn't put a piece of that, another conversation piece I wrote about that, but there are going to be issues in Greenland with losing draft in their ports. My understanding is the entire east coast of the U.S. Will see sea level rise. The amount of that rise will differ depending on exactly where you are and the glacial isostatic adjustment models you use. But at the levels of sea level rise we're talking for melting Greenland and Antarctica, the entire east coast of the U.S. is going to get its feet wet. So that's a very simplified, Guardian simulation of what will happen, and NOAA does the same thing. There's a sea level rise viewer you can look at if people haven't. It's a great teaching tool. But the glacial isostatic compensation and response around the world is much more subtle once you get away from Greenland and that ice.
Yeah, there are a bunch of good sea level rise viewers. NASA has one. I'll see if I can remember to put one in the chat. So one last question, very briefly. What has federal funding allowed you to do in your career?
Oh my gosh, federal funding has allowed me to do so much. I have mentored over 45 graduate students at this point, most of whom were supported by the National Science Foundation. And I can proudly say equal number of men and women. They are all employed at science at this point. They are all doing science that benefits communities in all kinds of ways. Very few are in academia. Most are in either government or private sector work or education work. It has allowed my group to understand the history of the Greenland ice sheet and its comings and goings. We've studied erosion around the world, which is absolutely important to folks. I am deeply indebted to the National Science Foundation for supporting work that I hope has made a difference in the world to people. And all of us live on our surface, and that's what we study. So I think it is an absolutely marvelous institution. It has the most rigorous standards of grant approval and vetting that I have ever seen. I've served on panels, I've served on advisory committees, I've seen it from the outside and the inside, and it is just a spectacular organization. And it pains me to watch now what's happening to 75 years of American science.
Yeah, I think you made a really good point, which is that when the government gives us money to do research, they're not only paying us to do research, they're also paying us to produce the next generation of scientists, because as anybody in academics knows, graduate students do most of the work. So, and that's how they learn to be a scientist. So we're not only doing research and advancing the frontiers of knowledge, but then we're producing the next generation. It's this self-fulfilling cycle, or the self-propagating cycle, that's incredibly virtuous and has really delivered enormous benefits to the U.S. And I agree with you. It's a tragedy to see it being hindered or dismantled or whatever.
And I'll add one more thing to that, Andrew, which is the NSF has funded us to do work around the world, and I think it has created a huge amount of goodwill in terms of science diplomacy. We've worked in South Africa, we've worked in Namibia, we've worked in South America, and lately we've worked in Cuba. And that scientist to scientist interaction of the peoples of the country has changed me as a person, and I think is just incredibly valuable, whatever we want to call it, American soft power. But it's diplomacy on a person-to-person level, and that is, I think, just invaluable.
Yeah, I 100% agree with that, Paul. Well, we thank you very much for that talk. That was really great in the discussion. And let's move on. So before I move on, though, let me just remind everyone what we are here to do. So thank you for joining us at, again, I don't know exactly what hour we're in, 25-ish of the Weather and Climate Livestream. We have about 75 hours to go. And we're really happy that you're here with us. My name is Andrew Dessler. I'm a professor of atmospheric sciences at Texas A&M. I'll be your host. We've seen some really excellent talks, and I'll introduce the next speaker in a minute. But before I begin, let me just mention that all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of other participants, their institution, their funding agencies, anybody else. They're just here to talk about what they do. But we are actually all here for a shared purpose. Americans deserve good weather and climate forecasts, the kind that saves lives during hurricanes, helps farmers plan their crops, and guide families making weekend plans. And I should point out that U.S. scientists have been world leaders in weather and climate prediction for decades. We developed the first computerized weather forecasts in the 50s. We launched satellites that measure the Earth. When you pick up your app and you look at what the weather forecast is, that's coming from government forecasts. It touches every aspect of our lives. Scientific excellence exists because of investments by you, the public. U.S. federal funding for science has been essential to maintaining America's leadership in weather, climate, and in fact, all aspects of science. If you ask why the U.S. is a world leader in AI, in GPS, in MRI, and medical technologies, it's all because of federal funding to universities. But now funding cuts could affect all areas of weather and climate science. We're seeing weather stations short-staffed just when extreme weather is becoming more frequent and dangerous. Climate research labs that have operated for decades are shrinking or shuttering entirely, taking with them irreplaceable expertise and decades of climate records. And so we need your help to save our forecasts. There's information about contacting your representatives, and it is going across the bottom of the screen right now. And I really encourage you to call your reps. They listen to what the people who call them say. They really do. They need to get reelected. House of Representatives, representatives in the House need to get reelected every 2 years. That means they need to get about 200,000 votes every 2 years. And so they do care what people say. And if you call, they're going to assume there's 100 people like you who just aren't going to take the time to call. So you have enormous leverage if you give them a call. And, I saw in the chat after I said something similar last time that people are saying, oh, my representative is crazy or something like that. That may be true, but still call. Even if you think they're crazy, they still are looking at these phone calls. And, it may not move them, but it might. You never know. So you got to try to do it. Okay, so let us move on to our next speaker. Our next speaker is Dr. Molly Robey. Molly is an assistant teaching professor of communication at Loyola University, Maryland, where she teaches communication courses as well as meteorology. She's also a PhD student in Earth and Planetary Science at Johns Hopkins University. She has a BA in meteorology from Penn State and has worked as an on-air meteorologist at AccuWeather, WJZ-TV, WJLA-TV in Washington, D.C. Her research focus is on science communication, education, and community engagement. So hopefully, Molly, all those facts about you are right. If not, please correct me. But otherwise, welcome. I really appreciate the talk, and take it away.
Thank you so much, Andrew. And I'm not a doctor yet, but I'm working on it. But thank you for the time today. I know I talked a little bit earlier today about more specifically my research goals and what I've been working on at Johns Hopkins, but I'm also a professor at Loyola University, Maryland in Baltimore, where, as Andrew mentioned, I teach journalism-based classes and also a meteorology course, which I developed with the help of one of my colleagues, Dr. Joe Ganem, in the physics department. So this class really was built from the ground up, and I drew a lot of the course and kind of my ideas from when I was at Penn State. Dr. John Neese is someone I admire and really met for the first time in middle school when I went for Penn State weather camp. So just a little bit of a rundown of what I'm going to be talking about today. The class itself is called Practical Meteorology. So we're going to talk a little bit about the class and how it originated and the process to really get that running at the university. Also, this year we launched Skyhound, which is our student-run meteorology. We're not an official club yet, so I can't say club, but we are organized, and there's about 8 to 10, maybe 12 students who are actively engaged there. And then I love to hear from the audience, so I'm going to save some time for some questions and answers at the end. This is a look at when we went to WJZ in Baltimore, which is where I freelance from time to time. So this is a look at a group shot when we were there just this semester. So I'm not going to spend a ton of time on my bio. You all know that I'm at Loyola, but I also freelance pretty regularly as needed at WJZ in Baltimore. A lot of my research initiatives are also run through the Earth and Planetary Science Department at Johns Hopkins. And at Johns Hopkins, I'm also a member of the Social Psychology and Education and the Environment Lab. That's run through Dr. Hunter Glenbach. We focus on a lot of education-focused environmental topics in our research. So Practical Meteorology, it runs through the physics department, currently at the university, working on environmental studies as a program that was just approved. But at the moment, the meteorology course is in the physics department, and it is an intro meteorology course. So we cover a lot of topics, kind of just scratching the surface from general synoptic weather patterns, highs, lows, fronts, to wildfires and other natural disasters. We spend time talking about hurricanes and tornadoes. So really just a broad brush introductory course. It's capped at 25 students. It fills every time it runs. It runs once a year in the spring. And it mainly consists of upper level students because it has become pretty popular at the university. So there's no prerequisite that you need to come into the course. And excuse me, the process to get it approved was pretty lengthy. So having to put together a whole application for our undergraduate curriculum committee to approve. So at Loyola, it was approved as a core course. So students who take the class get a natural science credit for really the core curriculum that they have to take at the university. So that's been really great for the course to run. And you know, when we first put the application in, it actually got denied because there were a lot of questions about, you know, what is the big idea with the course? And the big idea of the course is understanding the scientific method. So we spend a lot of time at the beginning of this semester identifying a question that we want to answer over the course of the semester. Each week, the students take weather measurements from our weather station on site at Loyola, and they are then able to kind of help answer that question, research question, by the end of the semester. So they compare things like temperature, dew point, wind, how much rain we receive, and kind of understanding the weather patterns as the seasons change. And so that's really the big idea with the class, but we're learning all different kinds of weather throughout that: radar, satellite, severe weather, etc. One thing I've also added into the course is real-world experiences, which the students have really enjoyed. This picture is a look at the solar eclipse in 2024. So we spent the day on the quad. There was probably, so if you're not familiar, Loyola probably has a little over 3,500 students, and the quad was packed with, I mean, hundreds and hundreds of students were there. So it was really a great experience and something that they will remember, hopefully forever. Another thing that, you know, kind of tying in those real world examples, as I mentioned, this year we did a wildfire donation drive. So this started as an in-class activity where I asked students to get into groups and really look at the wildfires that were current at the time going on in California and understand why they were happening, what they could do to theoretically help the situation. But as we were kind of going through our in-class discussion, the students really thought, you know, we want to make a difference. Can we do this? Can we actually put together a drive? So within 2 weeks, we had a full-on wildfire donation drive on campus. We had donation boxes. We partnered with Art Gallery in Baltimore, who they were getting a lot of media attention at the time. And we sent some supplies there. And then the other supplies, my students found a YMCA in LA that was accepting donations. And so we boxed everything up after about 2 weeks and got to send the physical goods out to California. So the students were given tasks from, you know, kind of our promotion team. You know, we need flyers to get the word out about this donation drive, to event services. Where are we going to put the boxes? Do we have permission to put the boxes on campus? To really just maintaining that relationship with our partners. Where are we going to send? How much do we need to ship? So from start to finish, this was student run, and I was kind of just their manager, project manager, making sure we were meeting deadlines and had the goods ready to go on time. So this initiative really got me thinking about their feelings about climate change. So at the beginning of the semester, some of them were expressing, you know, like, we know climate change is a real issue and we're concerned about it, but we're not really sure how to make a difference. And after this initiative, some of them said, oh, we feel like we really made a difference and we connected with people across the country that we never would have even been able to connect with. So that's a look at our group picture after we kind of boxed up all the goods. Another real world experience that's offered, we go on a field trip every semester to WJZ in Baltimore. It is a really great experience for our students because they, even if they're not interested in weather, if they're interested in TV news, they can see a real newsroom setting, how things happen. This semester, we sat in at the 4 o'clock news, so everyone had to turn their phones off. We were sitting very quietly off camera, but that experience in itself, they got to see the anchors engage with one another, and they got to see the meteorologists on staff do their thing, give the broadcast, and then also really understand what goes into it behind the scenes. So a lot of the products that we're using, you know, they originate from the National Weather Service. And what does it mean if we don't have access to those models and those graphics? And the graphic system at WJZ also pulls in kind of like PowerPoint is what I like to explain it, because you can set up your weather story in any order you would like. And so telling our students, it's also telling the weather story. What's the most important? What's the next important? What's going to impact the most people? So we get a lot of, or I get a lot of qualitative feedback about this experience, how much they like it, and they appreciate every time we get to go. Another big part of our class are guest speakers. So in the past, we've had Alex Wilson from the Weather Channel join us on Zoom. This semester, we had Taven Wooten from a Boston station join us via Zoom. And there were a couple instances this semester where I do try to bring in a National Weather Service employee to speak with us, but due to the current climate, they were unable to talk with us this semester. And, I like to do that because, yes, on-air meteorology is a popular field, but there's also a lot of meteorologists behind the scenes and working off camera and want to make sure our students are familiar and get a full taste, understand the breadth of the industry. And additionally, this semester, they worked on a hands-on activity assignment. If you saw my earlier talk today, I was talking about the Baltimore Community Weather Network. It is a series of more than 50 weather stations at this point placed across Baltimore City. My advisor, Dr. Darren Warr of the Earth and Planetary Science Department at Johns Hopkins, he's on the atmospheric dynamic team for the Baltimore Social Environmental Collaborative. Now I'm throwing a lot of kind of names at you, but it is a 5-year grant-funded project through the Department of Energy, and the Baltimore Community Weather Network consists of all the weather stations that we're putting out across the city. So my students in the journalism-based classes really helped develop the logo, the brand guidelines, the color scheme, the posters for the Baltimore Community Weather Network. And the Baltimore Community Weather Network, we have these weather stations at nature centers, schools, faith-based institutions, and we remain in contact. So it's really a partnership where they have the weather station on site. They're able to collect the weather station data. And what we're trying to do in addition to that is provide activities and resources for youth and all that come to the host sites to engage with. So this is a coloring sheet that my practical meteorology students helped create as one of the kind of leave behinds at the host site. Other activities for kids, one group did a bingo card of weather events, which I thought was kind of clever. Another group did a tornado in a bottle, so probably pretty familiar with everyone, but that was really cool because they actually took the time to make the tornado in the bottle, and then they gifted it to me, and it was really nice. So, even this, just giving them the ability to live beyond the class, right? So what we're doing in the class, yes, they get graded for, but it lives beyond. The Baltimore Community Weather Network materials are, really indefinite. And some of these activities we can kind of take to other host sites and do as needed as well. So that's kind of the practical meteorology class. I did want to spend just a few minutes talking about Skyhound. So Skyhound is a student-run meteorology club with a focus on keeping the Loyola community informed and prepared. Skyhound has been a work in progress for a long time, but basically I was needing students to really get it off the ground. So the meteorology course started running. I started kind of gauging interest. Do you all want to have some sort of club or group that really focuses on weather? And so this semester, myself and a few students, I think there was maybe 3 students at the time, the students said, we want to move this forward. We want to try to get recognized as an actual club on campus. And we reached out to our student-run radio station at Loyola, WLOY, and the director there gave us the opportunity to have bi-weekly weather reports, which has never happened at the university before. And the students were very excited to do this. So a student graphic designer at WLOY designed all of the graphics for us. So Skyhound weather forecast, that's kind of our brand, and the color scheme. The picture here is Tally Hayes. She's a student at Loyola. She was our first weather broadcaster on WLOY. So of course we had to celebrate and make sure that we gave them the recognition they deserved. So throughout the semester, we've been trying to get the word out. That's Tally there recording one of the broadcasts. We report Mondays and Fridays at 12 o'clock on WLOY. And again, WLOY, student-run radio station at Loyola, they run 24/7. So you can give that a Google and give us a listen. Our next kind of steps for Skyhound, we need to get recognition and approved through the Student Government Association at Loyola to be recognized as an official club. Once we're recognized as an official club, we'll be able to get a little bit of some funding to maybe help out with some gear and hopefully, propel us forward. We want to do maybe some recruitment on campus. We're thinking about doing, some watch parties with some weather documentaries and things of that sort. So this is really from the ground up. We're trying to get it off the ground, and this is a look at the group shot here. So we have, 5 students in the picture at the moment, but I'd say we are up to about 10 at this point. This was an event that we had a table at, and one of the students is a LaCroix representative. So really great for us because she brought some LaCroix to pass out at the event just to, spread the word about Skyhound. So we'd really like to get wider reach. There's plans in the fall to continue. Well, we're still doing the broadcast even this summer on WLOI, but really hitting it hard in the fall, getting that SGA approval. The Greyhound is our student-run newspaper. So we are in talks with them with maybe doing some broadcasts on the website. We do have Graycom Studios at Loyola, which is a full news organization, and they have a green screen and everything like that. So we're hoping to do some partnerships with them. And I also have to mention that AccuWeather's been really great in giving us their graphic system as an organization on campus. So we do have access to their graphics to use on the green screen wall, which has been great for our students to really get their first kind of feet wet and dabble in green screen work. But we're always looking for more partnerships. Mentorship is something that I'm kind of looking for the group. I'm the faculty director. The students at the end of the day have to want to run this and to move it forward. So I'm just here to kind of facilitate that and offer support. And always looking for other colleagues to look over some of their weather scripts. I'm only one person, but we have bi-weekly weather recordings. So anyone who wants to get engaged in that way, that would be, really helpful for the group just to make sure weather information is sound. And we'd like to take some field trips, maybe get some Skyhound gear. So those are kind of the next steps with the club. So I think that's pretty much all I have for today, and I'm happy to answer any questions. I very much value your time.
So thank you very much, Molly. That was really interesting talk. Let's all thank her virtually. Imagine 1,000 people clapping for you. We have one question in the chat that's been sent to me from Lily Coulot. From a sociology perspective, how do you think we could get society to care more about the impact of climate change?
Yeah, that's a good question. I think everyone wants to think of themselves, right? So a lot of these students, they remember, oh, I was in a horrible storm once, or, oh, I rode out a hurricane once, or, oh, I had a best friend that was in severe flooding. And so I think those moments are going to become more frequent. And instead of it being, oh, my best friend, or, oh, my dad, or, oh, a relative, it's going to be you that has been impacted by that. And so I think on an individual level, that's how we're going to get people to care, is that it's happening to everyone, which is sad. But I think that once they have a moment like that, then they start thinking about climate change a lot differently.
So let me ask a question about your class. So your class is called Practical Meteorology. So do you talk about climate change in the class?
We do. Yeah, we spend, we could have a whole class on climate change, but we spend about 2 weeks talking about climate change. And I specifically focus 1 week on talking about how climate change impacts marginalized communities. So understanding how communities that are more vulnerable are going to be impacted greater than those in non-vulnerable communities, and really understanding and getting the students to think about that. I got a lot of great feedback. We watched a documentary about Hurricane Maria in Puerto Rico. It's a documentary from PBS and kind of goes in detail about the government at that time and the funding and understanding kind of what went wrong. And so, yes, we spend time, but I could have a whole class on climate change. Yeah.
Right. So do you ever encounter students who are really like upset about climate change, and climate anxiety?
That hasn't happened. I would say in most cases, I was really feeling, I think most students are worried and they feel negatively about climate change in a sense of like, what can I really do to make a difference? And so I think what was really refreshing this semester was the wildfire donation, because we were able to feel like we were making a difference, or that they were making a difference in some kind of small way.
So if there's anybody listening now who's anxious about climate change, what would you tell them?
I read a really great book. It's called Not Too Late. And it was a whole, if anyone's familiar with the book, it is a series of essays about thinking about climate change more positively and how you in particular can make a difference. And I think that you have to tap into your individual, what you can offer. Like me, I am a meteorologist. I have a social presence. So how can I use my social platform to move the needle even just a tiny fraction on climate change? But great book if you want to check that out.
So we have a couple other questions here. One from Nico Tatara. Do you have any ideas, plans for more outreach to kids? Kids are great at influencing their parents.
Yes. Nico, I appreciate that question. So my first talk earlier today was about some of my research initiatives with Johns Hopkins, and it is all youth-based. So we are trying to develop these activities to get the youth engaged in weather in their neighborhoods. So think about these weather stations in their backyard or at their school. They're extracting the data, they're understanding the data, and then hopefully in the fall and spring, we're going to work to get them to broadcast their forecast from their school. And so, yes, we are very much, or I am very much focused on kids and know how important that can be. I think the caregiver piece is so interesting too, because through educating the kids, they're going to go home and say, oh, I went on this awesome field trip today at WJZ and I learned X, Y, and Z. And so there is some research out there to suggest that we can shift climate change perspectives in caregivers based on educating youth.
I think we have time for one more question from Ached Info. Do you think talking about vulnerable population kind of makes them think it is not affecting them?
Well, I'm not really sure about, what do you think about not?
Yeah, that question may not make as much sense as I thought it did when I first read it. Well, let's maybe rephrase it a little bit. It's like when you talk to people, what message would you have for a vulnerable population? What would you tell them to do?
Yeah, so the whole drive with the research through the BSEC and the Baltimore Community Weather Network is to tell communities in Baltimore who historically have suffered from segregation and past redlining issues. So many communities in Baltimore are still below the poverty line, might not have graduated high school. And so as we move into an era of changing weather and climate change is increasing, these populations need to be educated to understand those impacts and how they can be empowered to advocate for change for themselves. And so that's what we're really trying to do, is educate to empower.
So one question I just sort of have to ask, a little inside baseball, how much math do you have in your practical meteorology? Because that's always the challenge we have, that students want less math, but you got to have some math in there.
Yeah, that's a great question. So we talk a little bit about, well, I shouldn't say a little bit, synoptic weather has physics embedded in it, but we don't really spend a ton of time doing equations in practical meteorology. We kind of understand what makes the air lift and the highs and lows and the barometric pressure. And so since it is an introductory you don't have to have a prerequisite to join the class. Again, we understand, and I talk about the models and how the models have all these equations that are not solved and things of that sort, but the students aren't sitting there doing equations for the class.
I think that brings us to the end, and actually brings me to the end of my hosting duties. So I want to thank all the speakers that spoke in the last 2 hours. Those were all really fantastic presentations. I want to thank the audience. Really, it means so much to us that you're here watching. We toil away in obscurity, and so it's really glad to hear that people actually value what we do. And I just really encourage everybody to get involved. Exercise the muscles of democracy and call your representative, talk to your friends and neighbors, get the word out on the importance of funding. And I'm going to turn it over now to my good friend, Ricky Rude. We overlapped for about a decade in the 90s at NASA Goddard. And so I'll be really looking forward to hearing him host. So thank you all very much.
Thank you, Andy. And I assume that I'm online and people can hear me. And welcome to what, according to the left side of my screen, is the 25th hour of the Weather and Climate live stream, and there are only 75 hours to go. And we will soon be heading into the 26th hour. I am Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor, and I also spent 20 years at NASA, and I am the host for this segment. We've seen a lot of interesting and insightful talks so far, and this will continue to be the case for the rest of the marathon. A brief reminder that all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of all the other participants. However, we are all here for a purpose. We deserve good weather and climate forecasts, and U.S. scientists have been world leaders in weather and climate forecasting. In the U.S., we have built leading capacity in observing networks, advanced theoretical foundations, and provided state-of-the-art simulation capabilities. These simulations provide guidance that protect life and property and allow us to plan on time spans from hours to decades. Those who plan have the ability to anticipate risks and be more resilient in the face of weather and climate challenges. This excellence is because of investment by the public, and U.S. federal funding for science has been essential for our economy and security. Now there are funding cuts and threats of more funding cuts that are affecting all areas of weather and climate science, and we need awareness of the benefits of forecasts to help us save our forecasting capacity. We encourage you to call your representatives, House in the Congress, the Senate, as well as governors and others, because we need to maintain a presence and a constant vigilance of the importance of environmental predictions. And with that, I would like to introduce our next speaker, who is Erin Dougherty, who will be talking about precipitation and climate change. Erin, according to what I have here, is at the National Center for Atmospheric Research, where I am speaking from right at this moment. And I would like to turn it over to her.
Awesome. Thanks for having me here today. I'm really excited to present my work. And as was introduced, my name is Erin Dougherty, and I'm a project scientist here at NSF NCAR. Today, I'm going to be discussing precipitation and flood extremes. What are those present characteristics and what are those future changes? And before I get into that, I did want to talk a little bit about myself. So I've always loved the weather. Even before I was 3 years old, I would go out in the rain in my Barney umbrella and enjoy being out in whatever weather there was. And a little bit about my career path. So I am originally from Virginia, where I went to college at University of Virginia. I did my master's at University of Albany, and then my PhD landed me out west at Colorado State University. So I've stayed out here since my PhD, and I now work at NSF NCAR, which is a federally funded research lab. So it does depend on federal funds, and our main mission is to support the university community through a number of tools and the research we do. So our main mission is really helping other universities in the field to do atmospheric science and do good research. And so getting back into the research that I'll be discussing today, there's been a number of recent high impact flood events over the US. I've heard a lot of speakers already talk about Hurricane Helene in 2024, which is a really high-end example of extreme flooding. So you can see the aerial view of some of the destruction that happened. And then this rainfall map really illustrated just how rare of an event this was. So the rainfall totals were extremely high and actually made this a 1 in 1,000 year flood event. So this is a very high-end rare flood event, and it happened over the Appalachian Mountains, which, as you know, cause a lot of the rainfall to actually run off and cause flooding. Another example is some floods in Vermont in 2023. And so what's interesting, I talked about, in North Carolina and Appalachia, that was conducive to flooding, but also in Vermont, we know we have also mountains. And during July of 2023 in southern Vermont, we had really high soil moisture. And so we had this flood event that occurred due to a combination of this high soil moisture, and we also had really high rainfall totals, as shown here, up to 9 inches in some places. And so these flood events, we need to think of them not only from the atmospheric side or the land surface, but it's this combination between these two components that result in really devastating floods over the US. And you might be asking, okay, how devastating are these floods over a long time period? This is a really nice database by NCEI and NOAA that shows the billion-dollar disaster events over the US. Not just for floods, but also severe storms, hurricanes, but here I'm just focusing on flooding. So you can see, each year we tend to have a few of these billion-dollar flood events that occur, and the cost in billions of dollars, you can see some increases in recent years. So some of these flood events, they can cost up to $48 billion of damage to the economy. So we really need to care about these events in order to prevent economic loss. And as I mentioned, these floods are due to really complex interactions, which makes them difficult to predict, right? We know some things about the land surface, the atmosphere, the hydrology, but it's how they all interact together that makes these events really complex. And so what I'm going to focus on specifically is the precipitation that causes these floods. But just know that the land surface, that also plays a huge role in terms of soil moisture, snowmelt, and even land use. And then obviously the hydrology as well impacts what sort of flood response we get. So moving on, I want to discuss some work that I did during my postdoc looking at the causes of floods over the United States. And this photo is from Hurricane Harvey in 2017, which had really devastating impacts over the Houston metro area. So yes, as I mentioned, this was done during my postdoc, and this was funded by the National Science Foundation agreement with NCAR. So again, those federal funds really helped me to conduct this research. And the research that I'm discussing is looking at what causes localized floods versus these larger regional floods, which will obviously have very different impacts. And so to do this study, we looked at each of these gray dots is a different watershed catchment in the US. And these are one ones with natural flows. So that means they don't have dams, they don't have diversions. These are these natural streams that you think of when you think about streams. And we looked at local floods, which I'm indicating by this red dot, which is basically saying, okay, we have some event where the stream flow is really high, and it just affects one catchment. And we compared that to regional floods, which again has really high stream flow, but now it has to affect at least 25% of the catchments in one of these regions in the US. And from an economic standpoint, these are really the floods that are going to cause a lot of impact and a lot of devastation. And so really the goal of this work was to connect the stream flow and the land surface with the atmosphere. And so we identified specific storm types associated with floods, both local and regional. And so we identified things like fronts, extratropical cyclones, hurricanes, organized thunderstorms, so pretty large thunderstorms, and more of those isolated thunderstorms on those days that had really high stream flow. And then we also looked at the land surface. So on the days of floods or the day prior, we looked at, did that area have a lot of snow melt? Did it also have wet soil? Then it had this combination of wet soil and snow melt. Otherwise, we classified it as just having snow melt. Or if it had no snow melt, but just really wet soils, that's just going to be, you know, a wet soil type. Otherwise, it had no antecedent conditions from the land surface. So we looked at these combinations of storms and antecedent conditions on the flood days to see what are the dominant flood generating mechanisms over the US. And so we looked at this from 1995 to 2017. And what this is showing are bar plots. So the bars on the left are showing what proportion of floods are on the local scale. And then on the right is what proportion of floods are these larger regional scales. And we broke this down by those 9 different regions in the US. So there's a lot of storm types, a lot of colors, but a few takeaways from this, which I've highlighted here, is that you have many of the flood events, especially on the regional scale, are driven by fronts that are associated with these large organized thunderstorms. And this is especially true in the Mountain West regions, the Great Plains, and then also the South. Whereas the localized floods, we see a lot of differences, but the regional floods are really due to these mechanisms. And then we wanted to understand, okay, now that we know the predominant storm types producing the floods, what is the role of the antecedent conditions in combination with the storms? So again, we have these 9 different regions shown here, and now we're showing what combination do we have of antecedent conditions, and how does that connect to storm type? So where you have these thicker connections between those 2 categories means that accounts for more, greater proportion of these regional floods. And what's interesting, you see a lot of these pink bars connecting to these purple regions, which means that many of these regional floods we see over the US are due to some combination of having wet antecedent soils, plus some sort of front that's associated with a large organized thunderstorm. And I don't think that's too surprising, but it does make a lot of sense and gives us better understanding of how we might predict these floods based on not just the atmosphere, but also the antecedent land surface conditions. And so you might be wondering, how will the rainfall associated with these floods, how could they change by 2100? And that's important because a lot of city planners, people who manage dams and reservoirs, they need to plan how to update their infrastructure for the future in order to manage all of the water that we have in this country. And so you might be asking, how do we look at storms in the future? That seems crazy. And so what we can do is we can take this global atmospheric model, which is using physics and math to represent the weather that we see all over the globe. And we can take the conditions that are run by these models, which they run out to a really long time period. So in a lot of cases, they run out to the end of century at 2100. And we can take the conditions in 2100 and subtract that from the present day to understand what is that change that we might see. And then what we can do is we can feed this difference, so 2100 minus the present day, and we can add that to current weather data and feed that through a weather model. And what that does, as shown by this diagram here, is we are resolving smaller and smaller scales so we can get a better understanding of what the weather might look like in 2100 over, say, Missouri, at a pretty fine detail, which is really, again, important for people who want to understand those regional impacts. And so what we did, this was a study from my PhD at Colorado State, and we looked at these flood-producing storms in a future environment. So what we do, we identify the date and time of a flood-producing storm in a current climate. And so this is just showing you the upper level flow pattern, the upper level winds, and this star is showing where a flood occurred. And then on the bottom here, we're showing the surface conditions. So we're showing a lot of moisture is being flown into this region, which you might expect during a flood event. And then we see the winds are also directing that moisture. And what we can do, we can take that storm, we can apply those future conditions, which largely keeps the flow pattern the same if you compare these two panels. But now we're increasing the temperature and we're increasing the moisture. So we can look at how will that impact this flood event and its rainfall in a future climate by 2100. And so this is published if you go to the QR code here. And our findings show that in flash flood producing storms specifically, by the end of the century, we will see an increase in most places in the country by 2100. And so anywhere you see blue is an increase in rainfall from these storms. Anywhere you see red is a decrease. And if we average over the whole country, we see a 21% average increase in the rainfall from these storms. And obviously there are some areas of decrease, but mostly we are seeing this overarching signal of increase due to the fact that you have warmer temperatures and the warmer air can hold more moisture, which is fueling these more intense storms. We also looked at the rain rate. So rain rates are really helpful, especially for civil engineers, designing the infrastructure that goes into cities, that goes into your water management. And this is showing the distribution of rain rates in the current climate in blue, and then in a future climate in red here. And you can see that the whole distribution shifts towards more intense rain rates. You might expect something like 110 millimeters per hour of rain rates by 2100 in this study. And then you can also look at, how does the rainfall change per degree of warming? And we see that increase is about 10.5 per degree of warming that is simulated by these models. And so that's really important. If we see more intense rain rates, that means there's less ability for the water to actually infiltrate into the soils. And so looking at flood producing storms in the United States, we now know, due to this work that was federally funded, it is due to a combination of wet soils, fronts, and large thunderstorms that are all co-occurring. And looking at these storms that produce floods, we could see an increase of 21% in the rainfall by 2100. And as I mentioned, the more intense rainfall means there's less time for soils to absorb the rain, which means we could see more intense floods by 2100 as well. And so that's some future work I'm working on, actually looking what is the stream flow response we might expect with these more intense rain rates that we simulate in the future. And so obviously there's a need to keep funding this research in order to make sure that we're keeping our dams operating safely, our reservoirs, and to provide water to most of the country. So that is all I have. Thank you.
Thank you. That was a very interesting talk. And one of the things I'm sort of fascinated by is flooding and some of the discussion around it. I was very excited to see that you considered the surface and the antecedent conditions, because I think the surface is really important, both in the formation of the flood and then what happens to humans because of the of the way the surface, can funnel the water. When I write about floods in a public forum, there almost seems to be an industry that is trained to respond to tell me that it's not the rain that's causing the flood, it's the surface, it's the urban environment, it's pavement.
Mm-hmm.
How would you think about responding to that sort of statement? Because you've pretty clearly shown the importance of rain. So
Right. Yeah, as I mentioned, I mean, the land surface is really important, and that's where people live. So that's what most people care about, is the land surface. But as I said, it's really this interaction between the land surface and the rainfall and the precipitation that is really going to result in flooding. And I think a nice example of that is what we saw from the flooding from Hurricane Harvey. Hurricane Harvey made landfall in the greater Houston area. So being an urban area, there was a lot of pavement. So there wasn't a lot of ability for the water to infiltrate the soils, and it just ran off. But obviously, if we didn't have all that rainfall, a lot of the urban area was designed for much lower amounts of rainfall. And so that needs to be taken into consideration when thinking about the impacts, whether it's an urban area, whether it's a mountainous area like we saw with Hurricane Helene. We need to think about how the rainfall interacts with the land surface, and that will dictate where it will go and actually what will result in flooding. So it's really looking at this interaction that is very important here.
So a takeaway, it's important to think about the surface and the weather together, really.
Yes.
Yeah, it's hard to disconnect them. So a question that came early in your talk, at about 10 minutes in, is any of this data crowdsourced that you're seeing? It was from Mallow.
Yeah, no, thank you for that question. That's really great. So I didn't show this, but some of the flood producing storms that we identified to look at in the future, that came from the NOAA Storm Reports data set. And so a lot of that data set is actually compiled from people who, are driving around and they hit this flooded roadway, and they call that into their National Weather Service or to their local emergency response area. And then NOAA does a really good job of actually compiling all those reports into this really detailed data set. And so we based our study actually using some of those reported floods, which, obviously they came from people just being out and about in their environment and seeing things and noticing them. So it's important to have these reports from the public who notice these things, but also it's important work that NOAA is doing to actually compile all of these events that are happening into one database that we can use to study these.
Okay, interesting. I once reviewed a proposal about sensors on windshield wipers, potentially providing local extreme precipitation. Do you see any role for technology like that?
Oh, absolutely. I think the hard thing is sometimes the private data is much harder to access as a scientist, but that's where it could be nice to be in collaboration with some of these companies who might have data that is proprietary to understand some of these finer scale details on flooding that we might see and we might be able to use in areas that maybe aren't studied as well. So yeah, I definitely think there's an opportunity.
Okay. Another question from Rihanna, which is the idea of, can we start to change the perception of global warming to climate change to those who are more closed-minded on the topic? And I'd add to that, do you think that, what's sort of your analysis of global warming versus climate change? This has been an issue for 20 or 30 years in the field.
Yes, this is a really great question. I think there's actually a lot of work here for social scientists on how we communicate this message and how we get people to effectively respond to it in a way that, isn't divisive. And so, global warming and climate change have often been used interchangeably due to the fact that with increased emissions, we would expect, and we do see models simulate a warmer Earth just because we are, continuing to trap that heat. I think climate change is more comprehensive because that encapsulates not just the warming response we see with increased emissions, but it also encapsulates things like, the increased intensity of rainfall, the melting ice caps. And so I think climate change is a little bit broader of a term, whereas global warming is more specific. But again, I would love to hear more research about what social scientists are doing to effectively communicate those terms, and if there are better terms out there that could be used as well.
The late, great Jerry Mallman once told me that the mistake we made was calling it global warming and not global wetting. So
yeah, that's a great point.
Yes. So I'm going to follow up first with Ray Walker and the question on crowdsourcing, which is there a place to call to report this information to help in continued crowdsourcing? Is there some sort of an aggregator or something like that?
Yeah, that's a fantastic question. So I would say the best source is to call your local National Weather Service office. Another great way to be involved is to become a storm spotter. So this is something that I signed up to do in college. And it gives you a little bit of training on what do you look for when you're actually reporting some of these high impact weather events, whether it be tornado damage, flooding. Obviously, you don't need that training. Most people can see with their eyes there's flooding or there's a tornado. But I think, mainly calling the National Weather Service, since that's the direct route of information who will communicate this, is probably the best way to go. Yeah, thanks for that.
And is there a general number? Is your local office or?
Yeah, I would have to search, your local office, what those numbers are, but I'm sure a quick Google search could help you find what that is. I will say also a really nice tool historically for crowdsourcing information is also social media. So things like Twitter have been used very often to say, okay, someone reported flooding, we have the timestamp, we have the location. Things like that are also really helpful for scientists wanting to understand what's happening in real-time information.
Okay, thank you. The next message from the chat from 8info is, what about geological factors? And I think this means like being lower than sea level and underlying layers. And I would sort of add to that, having actually lost a house on the Chesapeake Bay due to rising groundwater. What is the role of the water table in maybe compound flooding or something like that?
Yeah, that's a really great question. I'm also sorry you lost a house in the Chesapeake Bay. That's a very vulnerable area. And so, there are places like the Chesapeake Bay, like New Orleans, which are technically either losing a lot of coastline or they are below sea level. And so that makes it much harder to keep the water out and to protect these areas. I think Miami has done a lot with boosting the infrastructure to help protect against some of these low-lying flood events, which you can get due to just the rising tides and certain ocean conditions. And so I don't specifically study compound flood events, but that is a big topic of research, is combining our hydrologic models, which can simulate, our rainfall driven floods or our riverine floods, and combining that with a coastal model that simulates the tides to better understand flood risks, even when you have a sunny day. And so I do think combining our models together will really give us a better picture of vulnerable areas for flooding.
Okay, and we've just very briefly got a moment before the next one. You showed that picture of Houston. And one of the things that I find interesting about the Houston area is the great efforts that I think it's the Houston Medical Center took following maybe a 1990 tropical storm to make themselves adapt and more resilient to that. So it's also a place where there has been some real substantive efforts thinking about how to deal with this. So,
Yeah, no, I think it's great that people are trying to take steps to mitigate against some of these potential threats that you could see.
Yeah. Okay. Thank you. Thank you very
Yeah,
much.
thanks so much.
It'll take me a moment to sort of get myself back together here. So thank you for joining us for the this marathon. I think according again to the chart I have over here on the left, we are at the end of this is the last part of the 25th hour, and we have 75 hours left to go. I am Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor, and I also spent about 20 years at NASA, and I'm your host for this segment. And we've seen many interesting and insightful talks so far, very much engagement from the audience, and this will continue to be the case for the rest of the marathon. A brief reminder that all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of other participants. However, we are all here for a purpose. Americans deserve good weather forecasting and good climate forecasts. We, U.S. scientists, have been world leaders in weather and climate forecasts since the beginning of the computational age in the 60s and 70s. In the U.S., we have built leading capacity in observing networks, advanced theoretical foundations, and provided state-of-the-art simulation capability. These simulations provide guidance to protect life and property and allow us to plan on time spans from hours to decades. And those who plan have an advantage because they can anticipate risks and be more resilient in the face of weather and climate challenges. This excellence is because of investment by the U.S. public, and federal funding has been essential for our economy and security. But now funding cuts are affecting all of these areas of weather and climate science, and we need to be present and have awareness of the benefits of the forecast to help us save our forecasts. We encourage you to call on our representatives, our senators, our governors, to help maintain a presence and a constant vigilance of the importance of environmental predictions. And now I will introduce our next speaker, which I don't exactly understand. Molly Robey's weather forecast is what it says. Molly gave an earlier talk, and I know that she has been a broadcast meteorologist in the Maryland region, where I lived for 20 years when I was at NASA. And I'm very familiar with many of the things you were talking about. And it looks to me like you will be giving us the U.S. weather forecast.
Oh, great. Yeah, thank you for the introduction. I'm very happy to be here. And yes, I have been forecasting and broadcasting in Maryland for some time now. So let me move on to the next slide. So just to give a little background for maybe those who haven't came to my earlier talks today. So I am a meteorologist, broadcast meteorologist, went to Penn State and got a master's degree at Mississippi State in applied meteorology, and got my first internship, part-time job, and then full-time job at AccuWeather in State College. So I worked there for about 6 years, and then moved to WJLA in Washington, D.C. Wanted to kind of hit a better work-life balance and start a family. So I left TV full-time, but I'm still a freelancer. I've freelanced in York, Pennsylvania, Pittsburgh, where I'm originally from, and now I fill in at WJZ in Baltimore. So that is a picture of me over the past year working at the station. I definitely prefer morning work versus evening work, but just a preference. And I also write a weekly post for the Washington Post Capital Weather Gang. So I write the Sunday forecast discussion, and just really have enjoyed being a meteorologist and forecaster and scientist. In addition to that, I'm a professor at Loyola University, Maryland, where I teach communication classes and a meteorology course. And I'm also a first-year PhD student at Johns Hopkins in the Earth and Planetary Science Department. So yes, I am here to give a little weather forecast for the US today. So This is a look at our surface map. This is issued by the National Weather Service. This is free and available to the public at the moment. As we can see here, it's been a very active pattern along the East Coast. If you're living on the East Coast, more specifically the mid-Atlantic states, we've been dealing with kind of rounds of rain for the past couple of days, and it's due to really a stationary front on the synoptic scale. So that's kind of lower to the surface, which has been really providing us with the cloud cover and the shower activity over the past couple of days. As you can see, this front kind of extends into the southeast, and we have a cold front, which is going to be coming eastbound over the next couple of days. Now, the southwest portions of the country look pretty quiet, but they are actually being impacted by some notable weather that we'll talk about momentarily. Kind of the dry spot on this map is in the north central, as an area of high pressure is anchored there, with another front coming into the Pacific Northwest. And I teach a meteorology class. I tell my students, we look at these maps, and I think it's very important as maybe someone who's not in the scientific community to be able to look at this map and identify some of the key features. You know, what does an area of low pressure mean? What does a front mean? What in this map designates rain? So paying attention to those keys, it can be really helpful in looking at this map and making decisions for yourself. So some of the graphics I'm going to show you today are courtesy of AccuWeather. We have a student-run group at Loyola called Skyhound, and AccuWeather has given us or sponsored our graphic system at the moment, and so that's where these graphics are coming from. So Thursday, today, along the East Coast, as I mentioned before, this kind of stationary front is providing for the cloud activity, although here in Baltimore, if you're in Washington, D.C., we've kind of gotten a break, so to speak, with some of that steady rainfall that has been really hindering us over the past couple of days. But what's to come? We have a cold front that is currently in the middle part of the country, which is going to be coming east, and that's going to usher in the chance for some pretty strong thunderstorms on Saturday afternoon. So it doesn't look like an all-day rain for Saturday, but if you are going to be out and about, some stronger thunderstorms could be pushing in after about 2 o'clock with some locally gusty winds between about 45 to 50 miles per hour. Now, as we move to the southeast, this front, as we saw on the surface map, kind of works its way southbound. In addition to that, our water temperatures in the Gulf of Mexico are starting to become very warm, as you would expect for this time of year. A lot of that moisture kind of gets slurped up into the southeast. You add in that front, the moisture from the Gulf and the sun, and you're going to get thunderstorms. And so that's why we have some activity taking place across the southeast. But some of these storms could potentially turn severe in a few places. So if you notice the orange area near Lubbock, Texas, and Odessa, I think that's Interstate 30. I can't really see that great on this map. But regardless, what I'm going to talk about next is the southwest part of the country, which is dealing with some extreme heat. And oftentimes in this part of the country, we have all of that warm, moist air coming off the Gulf of Mexico. We start to see a dry line, and it is a line that tells us where the warm, moist air is and the extreme desert dry air is. And we often have thunderstorms originate there, which does look like might happen here Thursday night in parts of western Texas. So downpours, large hail, isolated tornadoes possible, and yes, some gusty winds. The yellow areas also indicate where there could be some strong to potentially severe thunderstorms. Moving on to the southwest part of the country, they are extremely warm. We have some alerts that are going to go into effect starting tomorrow. So a heat advisory is in effect for portions of interior California. So think Redding to Bakersfield. And again, that's a heat advisory that goes into effect tomorrow. That's going to extend until 7 a.m. on Sunday local time. In addition to that, we have an extreme heat warning that's going to go into effect for Las Vegas, and that starts at 9 a.m. tomorrow through 11 p.m. on Saturday local time. Temperatures are going to be over 115 degrees in Death Valley, so some real heat going to develop in parts of the desert Southwest. But what's really interesting about the desert Southwest is that by Sunday, we actually have our first system, tropical system in the Pacific Basin, and that is Tropical Storm Alvin. Tropical Storm Alvin is going to continue to kind of weaken as it heads towards the Yucatan Peninsula, and it'll bring in some moisture to the desert Southwest region Sunday through early next week. So although they're hot and dry right now, looks like they'll get some relief by the end of the weekend. So those are kind of the bigger highlights for what's happening weather-wise today and kind of moving forward across the country. I did want to spend some time talking about kind of behind the forecast, how do I put together a forecast? And there's a lot of misconceptions still, I would say, in the TV industry about how meteorologists might be given the information, especially if you work on air, but that is not the case. So there tends to be a team of meteorologists who are constantly looking at the weather, and we all look at the weather models and are able to make our own forecasts. And the models and everything that's free on the National Weather Service website is extremely helpful and valuable for putting together our forecast. So what I like to do is I like to start with the forecast discussion. These are written by meteorologists at the National Weather Service. You can click into where you live. So I looked at the Baltimore and Washington area this morning because that's where I'm located. And it's going to give you a real detailed description of what's happening, a stationary front, low pressure. So again, even being able to familiarize yourself with some of these key terms can be really valuable in understanding the weather and what's to come. And I do tell my students, I have my students look at the forecast discussion when I teach my meteorology class. So to me, this is where I like to start because I like to kind of read and understand what's happening on a synoptic scale, synoptic being kind of closer to the surface. Also, the National Weather Service has an hourly weather forecast. So if you click in, it'll say hourly weather or hourly forecast. And this is going to break down hour by hour the forecasted temperature, the dew point, the winds. We can look at rain chances as the day goes on. I will say when you work at a station, you're going to have access to like a future cast. So a future cast is going to look at the models and give you a prediction of what rain and precipitation might be coming ahead of time. But when I'm not working at a station, I really enjoy this feature because I can look at the times and understand when there might be higher rain chances compared to other times of the day. So I'm going to show you a few other models that I look at, but I tend to have a weather record sheet that I kind of keep on hand. I will say now that I've been in the field for a while, I don't really print necessarily this out and go line by line. But when I was first starting, this was very helpful in writing down the temperature, the low temperature, the rain chance, just to really understand the weather. What I also really love doing, which I learned from Dr. Neese at Penn State and his meteorology course, is we would have to isopleth. We would print out a blank map of the United States, and it would have all the barometric pressure values, and we would have to draw lines of all the equal barometric pressure. And that just gives you an overwhelming sense of where the highs and lows are. So you feel really connected to what's happening on a synoptic scale. A few other ones. So I tend to look at the average cloud cover, the COD website, also free and available to the public. Tends to have so many weather models available and easily accessible. The that is the cloud cover forecast. So this is going to tell you the average cloud cover. Is it overcast? Is there few clouds, scattered clouds? This can be really valuable on a day like today where we have a stationary front. It's not an all-day rain, but people want to know, is it going to be sunny? Can I go to the pool? Or am I going to be dodging clouds all day? And so even understanding the clouds and communicating that to the public can be very valuable in developing your own style of forecasting. I think I have two left. So this is a look at the jet stream winds for today. And this also I pulled from some AccuWeather models that I have, but where we see the red shading, so those are going to indicate areas of very extreme wind. And so this is about like 250 to 300 millibars. And for those maybe not in the community, I heard this from, I think, Stephanie Abrams from the Weather Channel a long time ago. I definitely am I'm an admirer of hers. But she said that the atmosphere is like a cheeseburger. And I tend to tell my students that because it's something that they can connect to and understand. So we have multiple layers of the atmosphere. We spent a lot of time talking about near the surface today. But if we can go all the way up to the top levels of the atmosphere where the airplanes fly, this tells us where we have some very strong winds. And so the red areas are where we have strong winds today. This can be very valuable, especially where we have, if you remember, West Texas getting those strong to severe thunderstorms, where we have that extra lift and strong wind can signal where things could get severe and have greater impact to our weather there. And then lastly, looking at the 500 millibar level. So now we're bringing it down to about the kind of burger level, if we're using the cheeseburger reference. 500 millibar, we can look at areas of disturbed weather. This is look at vorticity. So just some areas of stronger energy, so to speak. So again, where we have the reds and the oranges can tell us where there's some extra lift or extra energy in the atmosphere. If anyone knows Bernie Rayno, he also was a huge mentor for me at AccuWeather. We would look at the 500 millibar level all the time, and he would talk about positive vorticity advection and negative vorticity advection, and just learn so much about understanding the atmosphere and having a lot of respect for looking at these models and being able to put your own forecasts together. So I just want to thank you for kind of listening today. I know I have a little bit of time, so I'm happy to answer any questions, but this is a look at me at AccuWeather. This was when we were filming a commercial, I believe. I was outside in the rain, and I look really weather prepared, but I was not in proper shoes for this, which is funny, but definitely have enjoyed my time in the industry. So thank you.
Wow. Thank you very much. So there are a few questions in the chat, and the one by Potts Rescue I'm going to start with because it aligns a little bit with one of the questions I was going to ask. First, in the middle of your talk, or towards the end actually, you mentioned, you showed a cloud picture that you said you got from some website that had a lot of free available information. And I was wondering if you could tell us a little more clearly, where does that come from?
Yeah, so I don't know if I'm able to probably drop the link in the chat, but College of DuPage, I believe.
Okay.
And yeah, I'm happy to drop the link in the chat after my talk, because I don't think I can do that while I'm doing this. But that website, and I did meet the expert behind that website last year. His name is escaping me, but all the GFS model, the European model, the NAM model, the HER model, all of that information is on that website, and it is accessible and free to the public. So I do show my students that website. If anyone's familiar with the EWAL website through Penn State University, also free and available to the public, and has a lot of the forecasting models available.
Which is a perfect lead into this question here is how could you imagine this easily accessed, publicly available weather information change if funding is lost? And the data being presented here is not data that the College of DuPage is generating. It's federal data in many cases. So
yeah, right. I mean, if you think about it, it's all kind of originating from the National Weather Service. It's just where you go to access that data might be a little bit different. So yeah, I think it should alarm people. It should scare you that, that could go away, because, where would we go to get the weather information is a valuable question to ask. And I don't know that I am able to answer that.
Well, yeah, if it's, it's sort of naive policy thinking for somebody, if they say, well, all this data is available all these other places, but it's all, its foundation
Yes.
is the federal government. And another site that has it specifically for hurricanes is Tropical Tidbits, which is a very good site for learning how to forecast. So the next question is I'll go with Jacques Camposanto. How's this raw data processed to create these beautiful maps?
Oh, that's a great question. I also am not the creator of these maps. I'm just the messenger of the maps. So I'm not entire. I can speak a little bit about the ones from AccuWeather. So when I worked there, we had graphic designers that would look at the models. So look at, something similar to this cloud model or the 500 millibar, the 300 millibar level, and then they would actually go in with their software and kind of piece together where the fronts were, maybe where the highs and lows were, and then they would put it into their product, which I'm not familiar with. But it was very interesting to kind of witness that, right? Like I'm going in as a broadcaster and I can see them actually create the maps like while I'm at work and kind of ask them questions and understand from an outsider perspective about that.
And so again, this is access to digital data from the government rather than maps,
Right.
that then people can interpret for specific goals or better communication. I think you highlight sort of a supply chain of IT professionals, scientists that are making this connection.
Yeah, and I think it's also important to think about, even when I'm working on TV, like the temperature maps, the wind maps, the radar, the satellite, those rely on data on the ground, getting the weather information into the system, and then the system mimics it and pushes out the graphic. And so one of the research areas that I'm working on is putting out weather stations in Baltimore. And so, those are all owned and operated by kind of citizens or people kind of on the ground. And that would be different than them being issued and owned by the government.
Oh, okay. So the role of the personal weather station. So
yes, but then it's also, if you have someone who's maybe not weather aware, where are they putting the weather?
Oh yeah, sighting.
Is it under a tree? So you also have to think about that. And are they willing to share their data? So
another data question from James Toomey, which is the satellite data being streamed constantly, or do satellites deliver it once a day?
Yeah, that's a good question. And there's some satellites that have limited time or designated times each day that they bring the visuals back for us to see. But for the most part, I think it's visible satellite that does not matter the time of day.
Yeah, so the geostationary and the polar orbiting would have, or probably different data stream,
right?
Downloads and downlinks and things like that.
And there's also a lot of filters now that you can put on satellites to still see and interpret the data.
Over the life of my career, one of the amazing things is from a launch of a satellite to the acquisition of first data has reduced tremendously. When I was doing my graduate work, I think it was about 2.5 years after a satellite was launched
that we
might see data from it. The next question will go is from Kelly DeLoach. Yesterday, in one of the talks, there was a discussion of storms that have large hail, and a field campaign that's underway right now, I think called Ice Chip. And so their question is, why have there been so many large hail events? And I see a camper there that might be susceptible to a hail event.
Yeah, that's a great question. And actually, you're not the first to ask this. I was out walking the other day, and my neighbor brought up the same question about the hail. And I was watching the Weather Channel yesterday, and they had a great graphic about the size of the hail and what wind speed you would need to continue to carry that hail up into the cloud.
Oh, yeah.
Which I thought was a really cool graphic. I don't know if I've seen that before. But I think it comes down to wind. So are we seeing stronger wind in these storms? And in addition to that, I would say temperature is a factor as well. Just because if we have a big temperature gradient, so extreme warm, extreme cold coming together, that could also facilitate the hail events. So I like to tell my students, they have a lot of confusion around hail and grapple and, understanding the different precipitation types. But essentially, you have a raindrop that starts at the top of the cloud and then crystallizes and kind of keeps flowing in this rotation. And once gravity wins out, then it's going to fall from the sky. So basically, it's just these hail events, they're spending more time in the cycle before they come down, so they're able to get larger.
So they have intense updrafts, right. Intense vertical motion. And I would say, a large hail event could be a lot of medium-sized hail, or it could be a smaller number of gigantic hail. So if there's more moisture available in these severe storms, there are many ways we can realize hail. I think a lot of people don't appreciate that. Along with severe storms like tornadoes and hurricanes, many of the insurance companies look at hail as sort of another category of major disaster because of its impact on agriculture in the Midwest. So I just want to make a comment. I know you said that you were writing for the Capitol Weather Gang. And one of the things that I've noticed over the last, 10, 15 years is the immense sophistication and improvement of weather analysis in many, many media outlets. And I think the importance of sort of the credibility of those outlets in comparison to some of the places on the web that just seem to be people almost making things up. So having folks like you who are credentialed and expert writing these in clear ways has been an enormous benefit. There's one more question from Kelsey Ward that is stated to be lighthearted, but have you ever experienced a funny malfunction on the screens while on air?
Oh yeah, there's too many to count. I will say one time at WJLA, a bird got into the studio somehow, and it was seconds before I was about to go on air, and the bird kind of nosedived in front of the camera, and I obviously, panicked and was very scared. I also was so my role was meteorologist, but I also did some reporting during the week, and I milked a goat on live television. I've had all kinds of just never knew what I was in for. I think there was a bear attack in Frederick County one time, and I was sent to cover that. So you really just don't know what the day's going to hold, and that's what I love so much about the the industry. And, Richard, you brought up a great point about, making sure that the information you're getting is correct. And nowadays, and I think this ties into the hail question, we all have phones. Everyone's out and about. Everyone can be a reporter or out there kind of telling people about the weather. And so just making sure that you kind of validate where you're getting information, and also validating on social media that these, photos and videos are in real time and they're not from a previous event.
No. Okay, so we're at time. It's time to move on. I think you said you were at Hopkins working on a PhD with Darren. So tell Darren hi. Haven't talked to him in a long time.
Thank you so much.
And thank you so much for an excellent talk.
Thank you.
So it's time to move on to the next talk. Thank you for joining us. And now I think the 26th hour of the Weather and Climate live stream. So there are only 74 hours to go. We've crossed the 25% milestone. I'm Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor. I also spent 20 years at NASA, and I'm your host for this segment. We've seen many interesting and insightful talks so far, and this will continue to be the case for the rest of the marathon. I want to remind folks that our speakers are appearing in their own personal capacities, expressing their own views, which may not be those of other participants. However, we are here for a common purpose, that we, citizens of the U.S., deserve good weather and climate forecasts. U.S. scientists have been world leaders in weather and climate forecasting. And in the U.S., we have built leading capacity in observing networks, advanced theoretical foundations, and provided state-of-the-art simulation capability. These simulations provide guidance that protect life and property and allow us to plan on time spans from hours to decades. And those who can plan have the ability to anticipate risks and be more resilient in the face of weather and climate challenges. This excellence is largely due to investment by the public using tax dollars, and U.S. federal funding for science has been essential for our economy and security, not just in weather science, but in many other fields of science. And now funding cuts are affecting all areas of weather and climate science, and we need awareness of the benefits of forecasts to help us save our forecasts. We encourage you to call your representatives and governors. We need to maintain a presence and a constant vigilance of the importance of environmental predictions. So the next speaker is going to be Duncan Watson-Parris, and he will be talking about the role of AI. My understanding is that he's an assistant professor at Scripps, and I will now turn it over to Duncan.
Thanks, Richard. Thanks for hosting and all your work in getting this set up. It's been a great exercise so far. So yeah, as you say, I'm an assistant professor at Scripps Oceanography at UC San Diego, one of the oldest oceanographic institutes in the US and indeed the world. And I will be talking here about the work we've been doing in my lab, accelerating climate science with machine learning. So I briefly just want to introduce and acknowledge the wonderful group of students that I work with here at Scripps. So in particular, my PhD students, Georgia, Lakita, Varan, and Sophie, as well as some masters and undergrad students who inevitably do much of the work. So, I think I saw Kate Marvel gave a great talk yesterday that I think really introduced the crux of climate modeling and understanding the climate and the role of climate scientists in trying to unpick and communicate the physical changes that are happening in the climate and that are driven by anthropogenic emissions of greenhouse gases. I think the striking thing for me, particularly over the last decade, is the pace of change and the fact that change is accelerating. And we've seen a number of extreme events, both in the Pacific Northwest, as well as mudslides and wildfires, particularly here in Southern California, just recently in the last wildfire season a few months ago. And, what I will try and talk about and try and highlight and communicate is the role in climate science in trying to better predict and understand the details of these extreme events. We know the big picture. We know broadly, that these will become more common, and we know why. But the details of when and where and how are still, being thrashed out. So I will start by giving an introduction to the specific component of the climate system that I'm interested in and that we kind of investigate in our lab, which is the role of aerosol particles and clouds in the climate system. I'll talk a little bit about model uncertainty. So we use climate models to unpick this system, and I'll talk a little bit about, at a high level, why there are still uncertainties in these estimates and projections. And I'll then talk about the machine learning aspect and how we're using that to emulate these climate models, both to improve the calibration of them, so to make them more accurate, and also for exploring different future climates. And then I'll talk a little bit about some future work that I'm excited about here and elsewhere. So machine learning is all the buzz at the moment, and you don't have to go very far to see headlines about the magnificent advances and leaps that companies such as OpenAI and Google DeepMind and NVIDIA are making in industry and other sectors in harnessing the power of kind of machine learning to take all of the information and the data that we've collected and digitized over the last 30 years and training models that are able to capture that and interact with us and kind of feed that back to us in pretty impressive ways. I suspect most people now will have at some point interacted with one of these large language models like ChatGPT or Gemini. I think your Google searches now include one of these AI summaries, and that advancement in those technologies is filtering into the climate sciences, and there have been a number of efforts around the world to try and harness those improvements to improve the way we do climate science and environmental science. There are a number of kind of initiatives and labs that I've highlighted here, some of which I'm pleased to have been involved with. And so it's an exciting time. This is, at some point, there was some kind of reticence, I think, in the climate science community that these tools would be useful. There was a lot of buzz, if you like, and maybe some skepticism that this wouldn't be a golden bullet or a silver bullet that would solve all of our problems. But I think it's starting to be recognized now that there is something there. There are useful tools that we can use and harness to make our projections better in the science that we do and make that quicker and more accessible to stakeholders and other end users. So hopefully I'll give you, I won't get too kind of down into the details of these technologies and exactly how they work, but there are a lot of great educational materials out there available for that. I want to briefly kind of introduce the role of aerosol in the climate system. So this is my research focus. And if we flash our minds back, or maybe not our minds, but try and imagine back to some pre-industrial state. So we often talk in the climate community about the pre-industrial, and we were imagining sometime around 1750 or maybe 1800. And the main sources of aerosol in that state of the Earth would have been from sea salt, dust, and other biogenic particles. And these aerosol particles are not like the spray cans, the deodorant cans that we use, but these are microscopic solid or liquid particles, and like sea salt or dust, that interact with the Earth and the climate in two very high-level ways. The first is that they reflect or scatter a little bit of the incoming solar radiation straight back to space. So there's a lot of sunlight that comes down to the Earth, And these particles reflect a little bit of that back to space. The bigger thing that they do is they act as the seeds for all of the cloud droplets in all of the clouds all over the world. And so just very kind of brief cloud physics 101, as warm air rises, it cools, and the water vapor in that air wants to condense. It wants to form a liquid, but it needs a seed on which to do that. You don't reach high enough saturations to just spontaneously form a liquid. It needs a little particle to condense onto, and these aerosol particles provide those seeds. So every cloud droplet and every cloud in the sky was seeded on one of these aerosol particles. And clouds play an outsized role in the climate system. They cover 2/3 of the Earth's surface at any given time, and they reflect about 1/3 of all incoming solar radiation straight back to space. So they play a really important role in balancing the incoming and outgoing radiation, which is one of the key things we think about in the climate. Now, if we flash forward to the present day and we introduce then a whole host of other sources of these particles. So primarily from the burning of dirty fossil fuels. So, when you see a big truck or a train go by and you see this plume of smoke come out, those are kind of particulate particles, aerosol particles that are very carbonaceous. But there might be other sources of particles from desertification, and these all interact in this complicated chemical soup, and they interact and they coat each other and they coagulate and stick together. But again, if we just take a very kind of high level view of this, the effect of these additional particles is twofold. So firstly, by adding more of these particles, we reflect a little bit more of that sunlight back to space. So we actually impart a bit of a cooling, because if we reflect more sunlight back to space, then less energy comes down and warms us at the surface. The other thing that happens, you might have noticed that my cloud just got a little bit brighter. And that's because as we go from a kind of pre-industrial state to a present day where we have more particles, we end up with more cloud droplets. So if we have the same amount of liquid water in our cloud, if we have more particles, when they grow, they will end up being smaller because the water is distributed across more particles. And it turns out that if you have more smaller spheres, you have a higher surface area, and that makes your cloud brighter. And so actually these clouds now are going to also reflect a bit more sunlight back to space. That can also affect the onset of precipitation. So again, if we very crudely think of rain as the cloud droplets growing so big that they just fall out of the cloud, then if we have smaller cloud droplets, then we might get less rain. And if we have less rain, then those clouds might live longer, they might last longer. And so we might end up with more cloud. And actually, as we go down this chain of processes, we end up with larger impacts on this radiative reflection that's going on, but also larger uncertainties. These processes, these changes to the clouds are very complicated and very nuanced and very difficult for our global models to capture very well. And so the coupling of all these things makes this aerosol cooling effect one of the largest uncertainties in our estimate of the effect of humans on this radiative balance. So this balance between how much sunlight is coming out and how much heat escapes is something, the technical term is radiative forcing, and CO2, carbon dioxide, is the main warming component of that. Methane and other gases play a role too. Aerosols, through all those mechanisms I just described, provide a cooling effect that offsets some of that warming, but the uncertainty in that is rather large. And so a lot of our work is trying to focus on how do we reduce that uncertainty. And this uncertainty means that it makes it harder to predict what's going to happen into the future. So here I'm showing one particular emission scenario. So there are many ways that humanity might get to 2100 depending on the socio-political choices that we make in the intervening years. And this shaded region shows our uncertainty in the physical climate response due to those emissions in terms of global mean temperature change. Now, this scenario was kind of designed in such a way to keep us broadly in line with the Paris 1.5 degree target. But as you can see, there's a rather large uncertainty. Now, what we do here in this work is ask the question, well, if we knew the aerosol effect better, would we be able to know what the warming would be at the end of the century? And it turns out that if we knew the aerosol effect better, and we found that the cooling effect that I just described is relatively small, it's not causing so much cooling at the moment, then this scenario will follow the blue line here, and we will unmask less warming as we go into the future. So we expect emissions to go down, the cooling effect will go down, but because in this case it's not such a big cooling effect, we won't get so much warming, and this scenario keeps us nice and not too much warmer than we are in the present. If, on the other hand, we find that this aerosol effect is quite large, that means we've been cooling quite a lot and masking quite a lot of warming. So as we go into a cleaner future, we unmask more warming, and we find this same scenario, this same set of choices that we as humanity make over these years doesn't even necessarily keep us below 2 degrees of warming at kind of 50% confidence. So this is just to kind of say that these processes and these details in the climate system don't change the broad strokes of what's going to happen, but it enables us, if we knew those better, to make more accurate and more refined choices and decisions about, how drastically we have to cut those emissions and how quickly. So I've spent ages doing that introduction, but I'll try and speed up a little bit, or maybe I'll skip a couple of bits later on in terms of the machine learning stuff. But this raises the question of why, given all this amazing work that you'll have been hearing about during this live stream and all of the fantastic science that's been going on to try and address some of these questions, why does it still persist? And I think fundamentally it comes down to a problem of scale. So, when I was talking to you about the global mean change in temperature over the next 100 years, we make those projections based on very fundamental thermodynamics. If you think of the Earth as an isolated body in space, then if you put more energy into it, which is what we're doing by emitting CO2, then it will get warmer, right? And that's very fundamental. It's very straightforward. But the exact rate that it gets warmer, we infer from these climate model simulations, which model the Earth and the atmosphere and all of these cloud processes that I just described over a scale of hundreds of kilometers. And in order to kind of make those models as good as they can be, we rely on observations and process understanding about the details of these clouds and these aerosols, which can be very fine-tuned. They can be very fine scale, from satellite observations, which are shown by these different colors, as well as in situ aircraft measurements. So people go and fly through these clouds and measure everything we can about their properties. So I'll briefly talk about some of the work that we've been doing on this end of the spectrum in terms of the observations. And then if I have time, I'll zoom back out and link those back to these large-scale questions. So one of the things that happens when, or actually a really nice example of this cloud brightening effect that I described, is due to ships. So when ships sail out over the ocean, you have this otherwise pretty clean environment that you emit a whole load of aerosol particles into from these big container ships. And it turns out that those leave bright trails in the clouds where those particles have made the clouds brighter, just exactly as I described. And those, what we call ship tracks, you can see them from space. And actually some of the very first Earth observing satellites spotted these back in the 60s. And we've been studying them ever since, but it tends to have been a fairly ad hoc manual classification and going finding these things. So the blue here is just to highlight one particular track. What we did was take some of those, a few thousand hand-labeled examples of these ship tracks and trained a machine learning algorithm to go and find more of them. So we said, in much the same way that Google will train a machine learning algorithm to go and to say this is a cat and this is a dog, we told this algorithm that this is a ship track and this is just a normal cloud, go find me more ship tracks. And once you have that, then we can run that model over the 20 years of high resolution satellite imagery that we have available and infer and then look at the whole period and ask, where are these ship tracks globally? How have they changed? How are they changing? And what we found in this paper here was something really interesting, was the fact that those ship tracks actually reduced markedly in 2020 when the International Maritime Organization reduced the emissions or put a cap, on the emissions of sulfur that the ships were able to emit based on the sulfur content in their fuel. And so we could see the effect of those regulations, which were for air quality purposes, on the clouds and therefore on the climate system. We also had another paper where we turned this around and we actually went and followed the boats. So we have GPS locations of millions of boats across the Atlantic, and we asked, where do those plumes of pollution from those ships intersect with the clouds? And so those are these lines here in this satellite image. So the false color here, the orangey color, are clouds. And the lines are where emissions from ships have intersected the clouds. And now we can go and look for invisible ship tracks. So tracks that maybe our ML model or human eyes don't see, but nevertheless are affecting the clouds. And so we, in this paper here, we found some really cool impacts of these invisible ship tracks. I'm going to skip over this step and answer the question which I alluded to earlier, which was about how do we use those observations that we have from satellites and from aircraft to inform these models? How do we make the models as good as they can be? There is a lot of physics that goes into these models, but there are still parameters. There are still choices we have to make about exactly how we fit the data that we have. And so one way we do this, or can do this, is by building emulators over our climate model data. So here is a selection of model output from one particular climate model that is sampling from, in this case, 3 parameters. I'm only showing 2 of them here. But there are 2 parameters which control how much aerosol are being emitted and how absorbing that aerosol is. And then there's something we can measure, which is the total absorption of aerosol. And so we have these different knobs in our model, and we can turn down how much aerosol there is or how much absorbing it is. But we want to make that match our observations, our measurements of the climate system. And so what we can do is then fit an emulator to those parameters such that we can now just choose any combination of parameters and ask, what would the climate model have given us for those parameters? And then we can do that. We can sample that hundreds and hundreds of times, or millions of times even, to find the exact right combination of parameters that would make our climate model look like the real world. And so that's one way we can use these machine learning emulators to make our models as accurate as possible and the best representation of the climate system. I am going to skip over a couple of details about how we did that and some kind of high-level results of doing that, and instead talk about another aspect of linking these climate models now back up to these questions of what the climate will look like in the future. So one of the things that we do with the climate model output is fit very simple emulators from the inputs, which are the emissions of CO2 and methane and aerosol, to global mean temperature. So people have done this for a long time. And this is one way that policymakers and economists will ask questions like, what is the economic impact of a change in CO2 in 2080? They don't necessarily go and run a full climate model because that's very expensive and a pain. Instead, they will use a very simple emulator that will give them a rough global mean temperature for that set of emissions. And there are a few different tools people use. And then if they want to know what the impact might be in a particular region, they might map that global mean response to the particular region. But if we're doing that, this is a regression problem, right? We're mapping one set of inputs to a set of outputs, and this is perfect for machine learning. This is exactly what machine learning does. And so what we did was develop some machine learning algorithms that take emissions of greenhouse gases as well as maps of emissions of aerosol, because it turns out it matters where you emit the aerosol, and then predict where a climate model would have given you what it would have given you for temperature and what it would have given you for precipitation at the end of the century, without having to run my whole climate model. It just, the machine learning model will tell you what the climate model will have given you. And it turns out you can do this very well. So the top row here are 2 different emulators and the full complexity model that they were trained on, predicting temperature for a totally different scenario that the machine learning algorithm hasn't seen before. And I think you'll be pretty hard pressed to tell the difference. So it turns out this one actually is a neural network. This is a different type of machine learning algorithm called a Gaussian process. And this is the full complexity climate model that took weeks to run on a supercomputer. These 2 took seconds to run on my laptop. And it allows me to ask, you know, where is it going to warm up? Where's it going to cool down under this particular scenario? And these models do a very good job of capturing a lot of the details of this climate model response. And they can also do this for precipitation and indeed extreme precipitation. I also want to very briefly then mention some latest work that we've been doing funded by DARPA to build a generative foundation model. So similarly to how you use ChatGPT to ask about your maths homework or to ask about anything else you might be interested in, we wanted to imbue these models with knowledge and understanding of the climate system such that we could ask questions about our data from one of these models and get robust, sensible answers back. And so I'm excited to be working on that with some computer science experts up on main campus here at UCSD. I'm just going to skip through the summary. I'm really excited about where this kind of techniques can lead us, and I'm grateful to all the funding that I've received from NSF and DARPA and Google and others. It really is crucial to have that basic research funding to enable these questions and to push our science as far as it can go, so that we can support decision making and best inform, you know, our route to a more sustainable future. So with that, I'll end and happily take any questions.
Thank you. And since you brought up DARPA, I think it's also worth mentioning that in the federal landscape, the Department of Defense is also a big player in funding environmental research. And of course, they have their own environmental observing satellites because weather and climate are very important to our defense activities.
Yes.
So one of the questions in the chat is, what were the earliest recorded reports of industrialization affecting climate?
Wow, good question. I think, okay, so it kind of depends how you define it. I mean, the smog in London, in Victorian London, was clearly noticeable, and there was some talk at the time of the potential for that affecting the climate. But as far as I'm aware, there were no measurements or no kind of validation of that hypothesis. The climate responds relatively slowly because the ocean is such a good heat sink. It stores a lot of the energy. I think one of the first key indicators was from the Keeling curve, which actually was by a researcher here, Professor Keeling, which has been continued by his son Ralph Keeling at Mount Loyola in Hawaii, where they measure CO2, and you can see a very clear and distinct increase in the atmospheric CO2 from industrialization, and then the changes in temperatures that followed in the following decades. What's interesting is those ship tracks I mentioned were observed. So the first satellites that looked at the Earth from space were actually put up by the U.S. Air Force, and they saw these streaks in the clouds, and they were pretty confused. They thought they might be Russian missile tests or something, and they went to ask some atmospheric scientists what these might be. and a scientist named Toomey recognized that this was a manifestation of a process that he'd been thinking about for a little while, about this brightening of the clouds. So I think that might be the first indication, depending how you define it.
So we're nearly out of time, but just quickly on the ship tracks, the reduction of the ship tracks were implicated as part of the description of the accelerated warming in 2024, weren't they?
Indeed, yes, they were. And we've done some recent research exactly looking at that question of whether that reduction in the cooling may have contributed. We did a large number of on climate model simulations that seemed to suggest probably not, or it certainly wasn't the only factor. So I think it's a somewhat nuanced question, and I think probably it's a mixture of internal variability plus this effect.
It always is. Unfortunately, we have to move along, though. I just saw a question come from Bob Hudson. I'm wondering if that's my old boss at NASA. So anyway, thank you for a very interesting talk. And the next talk is actually also on the search for aerosol invigoration in deep convection. So there's some continuity here. But first, thank you for joining us at the 26th hour of the Weather and Climate live stream, and there are only 74 hours to go. I'm Ricky Rude, Professor Emeritus at the University of Michigan in Ann Arbor. I also spent 20 years at NASA, and I'm your host for this segment. We've seen a lot of interesting and insightful talks so far, and this will continue to be the case for the rest of the marathon. A brief reminder, all of our speakers are appearing in their personal capacities and expressing their own views, which may not be those of the other participants. However, we are all here with a purpose. America deserves good weather and climate forecasts, and U.S. scientists have been leaders in weather and climate forecasting. In the U.S., we have built leading capacity in observing networks, advanced the theoretical foundations, and provided state-of-the-art simulation capability. All of these simulations provide guidance that help protect life and property and allow us to plan on time spans from hours to decades. Those who plan have the ability to anticipate risks and be more resilient in the face of weather and climate challenges. This excellence is because of investment by the public, and U.S. federal funding for science has been essential for our economy and security in fields far broader than weather and climate. But now funding cuts affecting all areas of weather and climate scientists are happening, more are threatened, and we need awareness of the benefits of forecasts to help save our forecasts. We encourage you to call your representatives and governors. We need to maintain a presence and constant vigilance of the importance of environmental predictions. And I'm handing it over to Nick Seiler.
Before we do that, we're going to do some tricky business of resetting the stream. So let's thank Professor Rude one more time. Okay, so we have to reset the stream because YouTube is not set up for us to stream for 100 hours straight. And so are you all seeing a link on your screen? wclivestream.com/watch. I know there are almost 1,900 of you here, and I want to see all 1,900 of you in the next stream for an amazing talk by Professor Andrew Winters about the jet stream and extreme weather. All right, so copy that link, wclivestream.com/watch.